Hey, welcome to Coffee Compiler Club. We'll see what happens today. Here to talk about compilers, language runtimes, type systems, register allocation. I got specifically asked a register allocation question today, and I figured I would lead with that, but the guy who asked the question isn't here. But he
He'll
asked
watch
it
the
not that
video.
long ago. Sorry.
He'll watch the video though.
I know, but it's easier if you're here. It said Yasser should be here as well. It says he's busy doing the same. I mean, I've told him do all this shit. He's busy doing all this shit. So here's the discussion. But like, yeah, he'll watch it later. It's fine. Well, I don't know. So I don't have to lead with register allocation. I don't have any good way to lead with it other than to talk about what I would do or in thinking about doing. And no, let me go set up Emacs for display. And then I'll mention if people care, and if you guys want to do something different, we can always do that. Let me figure out giant font for Emacs. It's not font happy. So given the obvious lack of silence here, whatever, I'm just going to go roll, and we'll see what
Just
happens.
press escape, then colon, then Q
Right? No, it's
exclamation
meta
point.
X something. It's rarely escape directly. That happens, but it's
I'm
usually
joking.
meta.
Those are VI commands.
Yes, exactly. Exactly. It's the whole wrong thing. So, as mentioned on Discord, I have this allocator style I've done a number of times over the years and refined it since grad school. So, I've sort of many large scale industrial strength register allocators I've done that are in active use in compilers around the world. Fine. This is one I've refined a few times and I really like how it's worked out. So, this is where I'm headed for. And I'm going to call it a Briggs Chaitin click collector. Let me get people's faces where I can see them. Um, it's based on graph coloring. It has the O squared graph coloring thing going on. Um, it's fully general to all sorts of bizarre chips. So every register has every def and every use has a bit set of allowed registers. So you just throw them all in a giant bit set. Um, In the case of split int floats, sometimes I do a separable flag saying int floats, and sometimes I just run them all together. Um, because it's everything has all bits for all registers, you can handle weird registers like in DSP chips. Not to mention Derek's setup, who also said he'd watch later. He has a bizarre chip. Multiple outputs fully supported, so you can output like add and a carry bit as a register to the carry flag, as well as the add, or combine div ram kind of things. Intel 2 address accumulator style ops, reg plus equals or op equals other regs, only two registers. One of them can be on the stack if you're spelling that way. You get all the Intel addressing modes. It's just no more inputs to the instruction. Do register pairs without too much trouble. I'm using splitting instead of spilling. The reason is because it's simpler implementation and it actually does a really great job. Um, the notion here is instead of declaring a store or a load, a spill store, spill load to and from a stack, is you're going to split a live range in half. But the split half might color to a stack, where a stack slot is just another register in the register mask of allowed registers. Coloring your stacks also means you get these tiny stack frames. So C2 is notorious for making tiny stack frames even when he's spilling. Um, and then stacking and unstacking your colors has this marvelous trick that really simplifies the implementation and speeds it up. So there's a couple tricks I do to speed it up. Many years ago, 20 years ago, I tried to get these published, and PLDI was like not going to publish it because the referees wanted to see a comparison between linear scan and graph coloring, and I was showing you how to make a faster graph coloring. And the faster graph coloring run the day in that it's in every JVM everywhere and everyone loves how it works, but there's no papers on it. It's got to be one of the most popular graph coloring compilers on the planet in terms of number of times the graph coloring gets called with no academic papers on it. It's like suck. Fine. Um, I do end up having two different formats for the interference graph. So the interference graph is n squared, and I get two formats. because it's one of the rare times when flipping the format mid-flight is just faster than wrapping one of the two. With the bit set gives you fast container. Do you exist? Are you in the interference graph already? And the adjacency list gives me faster neighboring, and I have to walk the neighbors a bunch. During building it, I have to ask the are you a neighbor a bunch? And when I'm building it, I have to walk the neighbors a bunch. Fine. Unusual. There's a bunch of unusual things. Splitting is one unusual thing. Stack slot coloring is an unusual thing. Liveness and interference graphs are built in one pass instead of as a separate pass to build your liveness, followed by building your interference graph, which is actually C2 builds liveness and then interference graph. And lately, I just folded them together because it's almost done in one pass already. It was easy enough to fold the passes together. So that's an unusual thing. Another unusual thing is that uh, register instructions that demand a single register, specific named register for a def or a use, will simply deny that register to their neighbors instead of interfering. And if you put them in the interference graph and don't deny it, you pick up this neighbor. But when it's time to color, the one dude who gets the one color demands it. So the neighbors just can't have that color anyhow. So somebody's going to spill. So you just say, no, you don't get the color. And then you don't get the interference graph edge. And it's the interference graph that goes in squared. And all function calls demand all fixed registers in their calling convention. So you get this hugely small interference graph. So in C2, doing Java, including all the very aggressive inlining I do, enough function calls show up that I get this, it's literally 5x smaller interference graph on average. And since that's the n squared portion, 5x is a big enough constant factor reduction that it's interesting. Um, After that, it's kind of stock
So is
graph.
that a 5x smaller n, is what you're saying?
It's the n squared gets divided by 5.
Okay.
So it's the number of interferences, right? So n is the size of the program, if you will. It's the number of live ranges you're going to get. You're going to get one per node, not quite, obviously, but you get you get a near fraction of the number per node. Oh, here's Yasser even now. This is, geared exactly for Yasser.
What's up?
Hey, we're just talking interference graphs
Nice.
or graph coloring. So read this section on Emacs because I just talked it through, and then we're doing random questions. And one of them is at the bottom, there's the divide by 5 number, which I'm talking through. So say half of all the nodes in the graph produce an edge in interference graph or a live range interference graph. That's not quite right. Fees all join all interferences with each other, all live ranges with each other. You get a lot of fees, so that happens. But you get some large fraction of nodes that are, here's Aaron, that are in the interference graph. Okay. Then it turns out that many nodes in the interference graph have fixed register sets they're going to go to. And this would be mostly from calls, but in the older Intel's multiply, divide, do it. There's a couple of places that you get these fixed registers. Weirdo small DSP chips, which I did a lot of in the beginning, and also 8086. I did this C2 actually ported to an 8080. I guess 8386 was the first one. I started with an 8086, but I went to a 386 before it actually hit the public. A lot of fixed registers. Fine. That means that by not putting the edge in the interference graph, you cut the n squared count of edges down. So the bit sets still took the max of the bit set. That didn't shrink. But when you go to the adjacency list format, your lists shrank by 5x, and that was a big chunk of the n squared. So the bit sets already get a giant divide on the constant factor because bits are so dense. But the adjacency list would otherwise blow up, except you shrink it by 5x by just saying, hey, don't count. No need to be there. So the interference graph has this top level format where there's a driver and the driver just says, make rounds of coloring. And if you fail split and then you're done. When you get a coloring, you're done. So that's the top level driver. The coloring is here, and it's build an interference graph. Sorry, build a live range, build an interference graph, and the interference graph is built in with liveness in one pass. That's unusual. And then you color. And then if any of these fail, you go again. So the top level driver is fairly straightforward. Uh, this is a reasonable choice for sort of a max, you're dead now. C2 has some, no somebody asked. I'm in full on lecture mode, so you have to interrupt me to ask a question. But C2
Go
around
ahead.
this point switches to a spilling strategy, which is super aggressive just to get the job done and quits trying to get clever. So one of the things that goes on here is to get a good spilling is that we'll spill gradually. And almost all the complexity is all tied up in how you split. And that turns into, do you make progress? And if you oversplit, you get a ton of spill code everywhere that you don't want to deal with, or it really slows down. You know, the generated code sucks because it's full of spill code. So you spill gradually and slowly. And then the whole point of gradual and slow is that you make some progress, but not zero. And if you accidentally make zero progress, then you spin rounds forever, making no progress until you blow up. So there's a bunch of tensions there on splitting. The actual graph coloring is sort of straightforward. Um, Here's split code. I'm going to save it or not talk about it at all, only because it's like a mile of heuristics. We can talk some through. They make sense, but they're not, it's like hard to digest the whole algorithm. So the algorithm starts by saying, I'm going to graph color. And and here's another interesting fact, I think, actually about graph coloring. So when you first come into a function to go graph color, round one, you will just have hard conflicts, like not required by law, but in practice, you'll have hard conflicts. And what's a hard conflict? I passed an incoming argument and register RAX. I have a call that uses an RCX. It can't be in both RAX and RCX. That live range has a hard conflict. It must split. You have a bunch of must split live ranges on round one. You're just going to split them. Okay. After you go through the I must splits, you get to a situation where you typically have some live ranges which are way, way, way beyond the number of registers you have. They're the cliques, they form cliques. They're just bigger than the number of registers you have. And you just must split somebody. After you do one or two of those rounds, the typical story is you have a number of cliques that have one more register than you have available registers on the hardware. And with a little luck and a little biased coloring, they'll color anyhow. Like the clique has more registers, but some people can get adjacent, can get colors, and they're not quite cliques. The near cliques can get near colors, and they'll just barely color. And then you go through a bunch of heuristics where you didn't quite color, but you're one register short of coloring. However many registers you have, whether it's 64, 32, or 16, you have slightly more neighbors than you have colors all the time. And so the heuristics are all into the, now you're into the, it's exponential, it's NP complete, you can't do it. And so you try to get some minor slow progress through coloring. All right. So top level graph coloring, run rounds, split.
My understanding was the way you usually break the exponential is to just call it somewhere and say, at this boundary, I don't care anymore. Just do something suboptimal.
Right. I'm in squared until I hit round 7. And then in C2, around this round number, I say, fuck it all. If you don't color, you split hard at every def and every use, and we just burn stack slots, and now it colors.
Okay, so there's no explicit rule of this is where you give up. It's just sort of the coloring has stopped working, cut the problem in half.
Yeah,
That may have been a bad cut, but it's probabilistically not the worst possible one.
it's not that it's not a bad cut. It's that when I split you everywhere, you will produce a value, immediately store it to a stack slot. You have an infinite number of stacks. When you use it, you'll load it and then immediately use it. And I will now get a coloring. So it will be done and you will color. You may have to split twice if you had enough bad overlaps, but I've never seen it go more than a second round after I start the what I call hard splitting rules.
How deterministic is that versus random?
The only random part is when I pull people off the coloring stack, it's unordered. it's totally deterministic. It just completely repeats identically every time. But there's no ordering given to the guys who pull off the coloring stack who aren't colorable. And so you can't really tell the probabilistic or not. I pick somebody who's not getting a color. I say, you lose. Now you split everywhere. Next go round, your live range is one op long every time. Doesn't take very many of those, and everyone colors. Does that answer your question? There's no randomness in the algorithm, but there is plenty of
Yeah, I think
enough
so.
complexity you can't tell.
I was just thinking about a pattern I've seen a few times in microservices where you spin up several copies of something,
Hmm.
and for reasons that no one ever gets to the bottom of, some of them are just faster than others on average.
Oh, sure.
So
I
I was
mean,
wondering if you could have a technique that's like, hey, I start up 16 of my service and then I kill the slowest six. And because there was some level of randomness, the ones that happen into nice JIT compiles survive, and the ones that
right.
happened into bad JIT compiles
That
find
one has
themselves at the bottom of the stack.
the whole thing going where you get profiling data that varies according to when random stack sampling happens and network packets arrival time and all kinds of weird shit, which turns into different inlining, which gives you better or worse inlining and performance.
Yeah. Run the same Java code on six machines. You do
Yeah,
not get the
same
same machine
performance.
code
Yeah, yeah,
necessarily.
It's
and not
also
the same machine.
dramatically more complex now on production hardware because CPUs are no longer uniform in terms of the
Yeah,
compute the, the compute
yeah. That's right.
chunks.
Right. If
Like
Amazon
Intel, for
decides that
example,
they want some hardware back and they migrate your process to a lame eco machine, and then you have the big load spike hit and your lame eco machine can't keep up, and you
but
think, wow, this one sucks.
even if your machine doesn't move from under you, if you end up on the efficiency cores for Intel now, those are actually Atom CPUs,
Right.
the
But that's
shitty
part
cheap
of why I
stuff.
like evolution. If every time I scale up, I add new servers randomly, and every time I scale down, I remove servers based on who's giving me the worst performance numbers. Evolution will find a whole bunch of niches that it's optimizing that I never thought about or even knew existed.
Right. But if Amazon is like, when you start up, I give you the fast core, and when you hit some idle state, I move you to an eco core. And then when you come around, you're throwing off as eco cores, but you always start on a fast core, you always end on an eco core. It doesn't matter. You're turning servicers, but Amazon is fighting that heuristic. That's what I'm theorizing is you're going to get hit with. Amazon will just fight you on that heuristic.
There's some really nice guides out there as well for benchmarking that give you basically a checklist of things to turn off, in the
Hmm.
BIOS and turn off in the OS. And it used to be like a list of 5 things, and now it's like 53 pages.
Oh, right. Yes, right. I
So
remember
if you want, yeah, go ahead.
Azul went through this round where they're trying to get reliable, fast, high performance for the machine for the high speed traders, and they had to do a bunch of kernel tweaks to keep like looking for low pause times. And after the GC was no longer the problem, it was a lot of kernel things were directly responsible for pauses that you could get like interrupt storms, put on a direct CPU that wasn't anyone doing any work, page zeroing, and I don't remember. But Gil Tenney had a big old list of them,
Yeah.
and there were a bunch of random oddball things you never thought about. Were suddenly like, hey, you took a 10 millisecond pause because you did a malloc, and the OS couldn't hand you a page for 10 millis or something stupid.
But it sounds like the takeaway here is I don't need to deliberately insert randomness at this point because the universe will give it to me.
Yes, you'll get plenty of randomness here. Now, having said that, like I said, it's deterministic. So when it fails, you fail the same every time. So it's easy to debug. Easy enough. It's a register allocator, so always a bitch to debug, but you can do something about it. So I was going to go through into the different phases here, um, because they're a little interesting, a little weird, but I don't know. People want to dive into that. This is going to get nitpicky, which I guess Yas or maybe Arthur might want. I don't know.
Let's go. So,
Do it, do it,
um,
do it.
yeah.
So this is stuff I've been working on for another project that I've been setting aside specifically for simple when we get there. So it's fairly well defined. It's not completely well done because I'll probably redo a bunch of stuff on simple to make it life easier. Um, Here is, for instance, an obvious candidate for a struct of arrays versus array of structs. It started out being just one thing, and then it kept getting more and more friends, and suddenly, yeah, maybe now it's time to be an array of structs instead of struct arrays. So these are all indexed by live range number. What's a live range number? It's a random number. It's not a register number. It's not a node number. It's a random number of things that are connected together that are going to eventually get the same register number, but they don't have a register number yet. So fees join their inputs and their output to the same register number in the same live range. They have to have the same register number. Two address ops on Intel like x plus equals y. The x is an input and an output, so that it has to be the same. Has to be the same live range number. Has to be the same register number. Same register number has to be same live range. So all the plus equal ops are all same live range. There's a couple other places you pick up same live ranges. A common one though is fee functions. So talking about these for a second, live range union find. That's what the UF stands for. It means I'm going to discover my live ranges on the fly. I'm going to give every new node a new live range number under the assumption it's not related to anything else. And when I come to a fee and some other places, I will union live ranges together. And as soon as I have a union find algorithm, I have to have a find call, which is right down here. But here's the new call. Give me a new live range number, live range plus plus. Here's the find call, which says, given the live range, look it up. If I found a winner or a loser, I roll it up. I do the roll up. So here's standard guy. You are the leader because there's no one else. So you're not unified with anybody. You're the leader. Or you were the leader. You're not the leader, but you point directly at the leader. So I can't make any changes, but I return the leader. I return you as leader. Which one is this one is? You are leader the other way. This one is now I have to do the loop to find the leader, and then I have to roll up to the leader. Standard target union find algorithm, except because it's done as struct of arrays or struct of arrays, it's externalized. And if I did this as an array of structs, I would say I would pull up some sort of live range thingy and have the union find buried inside of it. Fine. Register masks. Right now it's set at 64 bits max. I do Intel, I'm going to need more than 64. So this is another candidate for needing another element here. I need an array of longs for a bit mask. How many registers does an Intel that I intend to generate code for have? 32 integers and 64 floats? I don't know. Whatever that is, I probably need more than what I got. These are hints because I don't have any profiling data because I'm not a jet. Loop, min and max loop depth, spelling heuristic. Another spelling heuristic piece. I could have more spelling heuristic pieces except I haven't bothered them. Okay. So there's a data structure. Get a live range number from a node, which just does a lookup and does the union find as necessary. Debug version, so the printing functions don't collapse union find and hide a bug because I print in the debugger with toString. When I stop at a breakpoint, he immediately calls toString. ToString calls a pretty print. The pretty print says, give me the live range numbers, because from the live range numbers, I get your register maps and get your interferences. I get a bunch of stuff I'm going to pretty print at the same time. If I do my roll up and I have a bug in my union find, the act of stopping the debugger calls find, hides the bug. So I have to have a version that is side effect free. A little bunch of utilities just give you a flavor of what's going on here. There's like and mask. Oh, look at this. This needs to go away. Oh, this is left over from the other guy. Basically, it says, I found another use for an existing live range. Mask their masks together. They have to take the constraint from both of them. And if that went to 0, I failed. Otherwise, I hang on to the constrained live range. And there's more things. So this is where the union might happen, and you have to pick up the union of the constraints, and I have to pick up, here's the and of the left and the right-hand side, they get union, and then the min and the max get union, and all kinds of shit happens because the heuristics gather this info. So it's ignoring that for a second. Let's look at like the main sort of thing here. Where's the good place to
So I
start?
assume when you say char, you're just using that as a uint 16 or something?
Yes, when I say char, the goal is to say, I want a named integer type that I know is small that will give me an error in the compiler if I mix it up with a normal int.
Cute. Yeah.
So
I love that Larry Wall comment that you can write assembly in any language because I'm looking at this and I'm like, you can write C in any language.
that is correct. And guess what? This has been written in C code by many folks over many years.
No,
This is
I
a,
meant it as a compliment.
I understood. This is a low level bit twiddly algorithm. That's what it is. So there's low level bit twiddly things going on all over the place.
Yeah.
Okay. So one of the games I'm playing here is that the register allocator has a bunch of globals, so I don't have to pass these things around everywhere, and I reset them between calls to register allocator. If I was to make this go parallel, I would make them a threadable storage. Or I might end up passing them around everywhere, but that's a
A
future
con
me problem.
or stick them all in a context and pass the context or something like
Yeah,
that.
that's what I'm saying. Pass them around everywhere would be put them in a context. Yep. I would call it an environment, but yes, something. The register allocator, like this is one of these classes is abstract, and I would just make that a non-abstract and make one pass it around. Fine. There's a bunch of reset games here, and then we have sort of the main player here for building live ranges. So what building live ranges is going to do, it's going to look for every def and every use of every node in the graph and find those live range register masks and set all masks accordingly. And anybody who's connected by the same live range around fees or two addresses will be union find together. So at the end of this, I'll have a set of union find live range numbers. They'll have been compressed because the union find always picks the smaller, and a set of register masks, one per active live range that, tells me how I color things. So you should be a machine node. A machine node is something that didn't happen yet in simple that converts from idealized to machine ops. Machine nodes support an input and an out. Hey, that's a better answer. We have, and actually, I know Matt was curious at this. So this is sort of a minimal, what I need to port on a machine. I need two things. I need this, something to name registers. I need calling convention, and I only have half of it here, so I need the full calling convention. I need a way to create a split op, and a split op is a move from reg to reg or reg to memory or mem to reg. And I'll just encode it differently if it's a load or a store. But from the register allocator's point of view, it's a split that happens to target both stack and registers. I have to lay out games. I'll have empty basic blocks when I'm done or not. So I have to have a jump op or not. I have an infinite loop handler here. It's a cheesy jump. Each individual machine op has an input register mask, given an input number on the node, return me the list of the set of allowed registers for that input. Currently set it along. If I'm on an Intel, I probably need more bits than along. Same for the output. Sometimes I have multiple defining ops. I'm producing a div remainder. And so I need to have a projection, one node per defined value in the SSA C of node style. The defined value might be the one that comes for the div or the one that comes for the remainder. And they go ask their div mod instruction, what register am I allowed for that particular guy? Whether or not I'm a two address op. Intel special risk ops generally need not apply. Are you cheaper to clone than to spill? What's your encoding? I have a couple different ways I might do this. Intel has these encodings that vary wildly in size. So my current theory is I'm going to have an array of bytes that I'm going to hand you. And this is like it's just an array list that's taking bytes. And it'll resize. So I don't know, byte buffer, direct byte buffer, heap byte buffer. I don't care. There's a number of things that might go there. and he'll just append and tell you how many bytes he took. And then there's some way to go pretty print the thing. Fine. So that's probably pretty close to what I need for portability of targeting whatever I'm going to target here. And then, of course, I need a mapping from nodes, ideal nodes to machine nodes. And that'll be a call on the machine guy, which is in here now. That'll basically, I'll take the stop node and walk the graph. And what'll come back is a replacement for the stop node that points to the replacements for everybody recursively. All right, so back to the building live ranges. If you're a machine node and you produce a register value out, so 0 is the uniformly, I didn't make it. Maybe your to address, and in larges 0 says, oh, I haven't given you a live range number yet. You do produce a value. You do not have a live range. You need one. Okay, if you're to adder, then you come down here. If you're not a to adder, get a new live range. And all register masks are allowed. And if you are a to adder, you take your inputs to adder. You're that live range over there. I'm an add of Rax plus equals RCX. Well, Rax is already got a live range because I did the prior guy just a second ago. So get his. Set your live range. Now you have a live range. And modify your mask according to what allowed registers are allowed. And then that was, I walked your inputs. Now I'm going to walk your outputs.
And the -1 is a placeholder for, hey, this needs to be cleaned up?
No, it's a placeholder for all bits. A new live range has a mask that says what are allowed bits. So this code went around a couple of layers. I almost could put mog.outreg here, mock.outreg because this is what set of live ranges you're limited to when you produce a value. Except that I have to still mask you if you're a to adder. So I hacked fast and I ran away and I added the to adder, the second one after the to adder pick. If there are no to address ops, but you also have interesting constraints, I could skip this step and just put the output here. Right? This live range is constrained to be in this set of registers. And unfortunately, if you're to adder, you take the limit of your outs and your ins and the other guy's already constraints. So you have to accumulate constraints, which is why I just did it once down here. I don't need to do it twice. It's just an anding operation. So 2 ands in a row is the same thing. But if I go to the, I'm a to address op guy, I'm on this line, I don't call the outrec map on the question mark side of the question mark colon.
So the and mask is a mutating operation?
Yes, it is and in place. Oh, because I didn't do my tags on this guy. It's this. We looked at it just a second ago. It's literally read from R masks and set into R mask. Read, modify, write into R mask, anding as you go. With a fail out if I ran out of registers. So what it means is that building the live ranges will die if I have conflicts between my inputs and my outputs. This is what I call a hard conflict, and it will force a spill. I won't go to the later stages of register allocation because I have failed already building, just finding the standard set of things. So a live range here of this mock node is presumably a call. He takes one of his inputs as a standard argument, a standard call argument position, say RCX. His input came from the return of a prior call, which is an RAX. RCX and RAX are both hard fixed. They're 1 bit in the bit mask for each. Those bits don't align. I get no bits. When I and mask, I have to spill here. Okay. Then there's look in the opposite direction, which is where I am looking for whether I'm going to, what is this one doing here? I have a lot of these things that are heuristics that are thrown in. Take my input. Oh, this is my output, and this is my input. Yep. So take my input mask, not my output mask, for every input. and the input exists and it's not memory and the mask does something exciting, go and mask that guy's live range. So for instance, I have an add of RAX plus equals RCX. Well, RCX is another input. And the add up may be really generous and say I take it on any register. CX can be DX, EX, SI, whatever the hell, R15, R99, I don't care. But I have to put that constraint on the guy that produces RCX because he might have a production that says, I only produce it in R2 and you only can and mask on R3 or not or something. So I'm picking up from a node's his inputs constraints for every input. And then the first stands up here is the output constraints, which says I produced a value for everyone below me. This is what I produced it in. I produced it in this register. You have to honor that. Oh, if I'm two adder, then I have to match above and below. But if I'm just producing it from whole cloth, here's the value. Here's the register mask. And then I have a couple cutouts for other things. Your fee node, I ignore memory things. Grab your live range, and then I have to go around the world of all inputs to a fee and unify them all. And I have some crazy, super optimized, not necessary list here. I'll probably clean up for simple, but one pass to see if any one of my inputs has already got a live range. If so, they all have to have it. If not, make one. And then walk again saying, here's the chosen live range. Y'all all unify with it. So this the set large is like set this and this and this and this and this, all to the same live range number, including gathering up all the constraints and failing out if I run out of registers and all that kind of stuff. Multi-reg is I produce multiple values. So that means I have a series of users. The users are all projections. I look at every projection. Projection will tell me where to get his live range and if he's a pass-through. Like if I'm an old school, div and brim, I have an input in RCX, I have an output in RCX. It's the same input and same output. I probably pin them together. Otherwise, the output projection just goes and asks the defining div rem node, hey, if I'm the div part, what are my register choices? If I'm the remainder part, what are my register choices? If I'm going to add with carry, if I'm the flags part, what are my register choices? If I'm the add part, what are my register choices? That's what's going on here. This is the end of for all nodes in the control flow graph. And so that's all basic blocks and then for all nodes. So at the end of this, I have visited the whole program. This is one pass of the program, visit every node, do something exciting. Make another pass where I look for everybody who's got a live range defined and roll up their union find, just so I don't have to deal with union find later. All the union finds get found back immediately to their leader. Then I look at a self-conflict situation that's a little weird. This shows up in code that looks like Fibonacci, where you're rolling two values, the unrolled Fibonacci, where you're rolling two values around a loop. So you're adding X and Y, and then you move Y to X, and the sum goes into the X plus Y or whatever. You carry a value with a copy around a loop, which you end up with these two fees that connect one to the next. And they're the same basic block, and they're two fees, and they join to each other. So the normal thing you do with fees is you just join their inputs and their outputs. So they're all joined in the same live range, but there's two fees at the same basic block with the same live range. That's another version of a hard conflict. That's what I call a self-conflict. Has to split again. You need a copy around that loop. So comment here, check for self-conflicting live ranges, and you will fail if the two fees share the same live range. There's a little cleanup on the failed set that I found late in life that basically says if I have a union find in the failed set, union it up and just collect the fails. So one pass through here will get me, generally get me a set of failed things. Fine. I'll need to go split and go again. If not, I've done my building a live range. I have a live range number associated with every node. Many nodes will share the same live range. That's pretty normal. There will be no hard conflicts, meaning every live range is allowed at least one register. Um, maybe that's the set of things I found. And then I collected some info about loop depth of live ranges and the like for splitting heuristics. And then I'm going to build the interference graph and we're going to color it. And build is weird in that it does it in one round instead of in two. I build liveness and interference in the same go. So what's interference graph? It's another abstract class. It's another candidate for struct of array versus array of struct. It does have a couple things here that are interesting. There is a set of live outs as set of nodes that are live out of a basic block. So it's indexed by basic block number, not by a live range number. It has a work list of basic blocks. It has a temp that I'm going to keep resetting per basic block when I do something. It has a triangular array of bit sets indexed by live range number. Some gathered data for spilling heuristics and registers per live range number. So a bunch of data structures, global, so I don't have to pass around a context, but maybe in simple, we'll deal with that at some point. Here's the build algo. There's a reset all my temps. That's just reset code. Push every basic block on the work list. Till the work list is empty, pull a block off, do a block. I succeed or I fail at this stage as well. And do a block is exciting. So because it's liveness and you have loops, you can't do it in one pass, top to bottom or reverse post order or anything like that. You must make more than one pass. But you can do it incrementally and do it only per depth of loops. So it's actually still linear in the size of the program, but it's not one pass. And that's weird because liveness is usually done in a like a reverse post order, but you need one pass per loop nesting depth. But you can do it incrementally, still RPO to start with, and then after that do incremental, and it becomes the size of the program depth for only the depth parts in the middle. It turns out I can compute interferences while I'm doing that because interferences stack. Same as I add more things to live sets, I pick up more interferences as I walk. So one fewer passes in the allocator because I can build live and I can build interferences at the same time. So what's a block do? Block says I have some live out. So the comment here, walk a block backwards. Key. This is a backwards problem, backwards flow. Walk a block backwards means I start with the live out of the block, which I got from prior blocks. And then I'm going to walk upwards. And when I find things, I'm going to do nodes on them, called do node. When I'm done with a block, so here's the backwards walk. Walk the block with inum minus minus there. That's a backwards walk over the instructions in a block. And then when I'm done and I've walked backwards to the top of a block, I now go to my prior blocks. What I have live out here is now unioned as set union with the live outs for the other blocks above me. So merge live out happens. Usually you have one parent unless you're a merge point coming down, then you have two parents going up. And then do node. This is one node in a backwards walk, and he has a bunch of shit he's doing. So there it is. It's kind of big, and then there's a bunch of comments and stuff at the helper functions to do. But it's not, again, it's not the end of the world, but this is, large, complicated graph coloring has a lot of things going on. So I got a node. I'm walking backwards, trying to compute live out. I'm defining a node right here, defining a value. That means that this def kills something that was live from below. It is no longer live because it's defined right here. So get your live range. Oh, you lived. Call self-conflict to check for self-conflicts. This is a fail point. Or kill the def. Go to my temp set and null it out. You are not live. So I've copied the live out set to temp so I can mutate it in a place because cache efficiency and code and whatever, it's easier to do it this way. Conceptually, people might want to think about it as I'm updating the live out sets directly, except I can't because I need to compute a new live out for the block and then union it into the parents of this block. but the old live out needs to stick around in case I visit this block a second time. So I do need to make a copy of the live set. Heuristic for spilling, just copy some data. A weird thing, if you're a copy op, which is true for all spills, you don't interfere. So I can kill one of the sides, the other side of the copy here. And now I have to do interference graph building. And then I'll make live. So when I came up from below, I defed, it killed something, killed a live thing. In a minute, in the stanza below the screen, I'll visit all my uses and they'll all become live and get added to the live set. So that's how standard live works. You kill your defs and then all your inputs became live. In between, I'm going to build interferences here. So I grab an interference mask. Your set of registers allowed in this live range. I have a special cutout called must define where I'm going to do this hack where I say, you must define this value. Therefore, there's no point in anyone else having that register at this point in time. They can't have it. So somebody has to die right now. So I'm going to yank the register out of their set. We'll get there in a second. Go visit all my live things. There's a union find hack that has to happen because I can't get it clean in one pass. So I tried to before, but it didn't quite work. So I have to do a union find hack. Then, are you actually live? Because this is a poor choice of data structures. This one actually should be a hash map, and then I don't need this test. And again, that's a thing I'll probably clean up at some point. But I look and see if you interfere with each other. So is this live thing currently live? So look, visit all my current live things. I'm defining a value. Is it going to interfere with something that's currently live? If so, then I want to add an edge to the interference graph. Or if you're must define, I'm going to yank it out of your choices, the current live guy's choices. And add interference basically does what you think. It triangulates on the bit sets and picks the smaller live range number, goes to his bit set and sets a bit. It's pretty straight up. Then the second half of doing live, which is visit all your inputs and make them all become live. So for all inputs, get a define, get a live range. So there's a lot of things that don't count and get rid of here. Check for spills, record for splitting heuristics. Check for self-self conflict. Again, you can fail out on yourself here. Now look for the reverse of what I said before, where you must define a single register. If you must use a single register at this point in time, you must have this value in RCX, no options. Therefore, no one else can use RCX. So I'm going to walk the other guys that are around. And so you're defining a single register, walk the other guys, do the union find roll-up thing. Okay, it didn't happen. And get the other guy who's live, get his mask, the masks conflict. Then I want to yank him out of the other guy's mask. Where did I not do it? Oh, look at this. So this is probably a bug. Of course, the allocator runs freely here. I was supposed to have updated. Well, there you go. I'm doing code review on my own code. The other guy's live range. And then if he goes to 0, you just fail and you have to spill. But I should yank him. If he doesn't go to 0, I'll just yank him. Okay, so there's a and then I set the input live by throwing it in my temp set as here's the def, and it's live until I run into that def, and then the def kills it. But I have a use. The use has a def. It's live until I find the def.
Since you're defining interference graph stuff right now, I'm actually curious about something. So I'm realizing now, like as I'm looking through your code, I'm realizing that the way that I was doing the interference graph when it came to register mass is that I would have a bunch of fixed like live ranges that were like basically bound to the registers to say like you interfere with the fixed form of whatever register, like let's say REX. So now you can't use REX ever because that thing won't spill, and so you have to spill.
Right.
Or you can't use it basically. And so
that's what's going on right here.
Okay, wait, so wait, are you doing that there?
That's must def right here. If must def, up here, must def. You're an op, you have one register in your output mask.
Oh, sure.
Okay,
But like, let's say you had like 2 registers, what would it do then? Because in my
Then
set, what
then
it would do is
because
you would interfere with every other like register.
Yeah. So I go to all things that are live. So I walk my live set. Here's my currently live in the current basic block point. And the register masks overlap. So if they don't overlap, they don't get an interference.
Yeah, but not. I don't think that's what I'm getting at. So let's say I'm coloring something that like I've got, I don't know, 16 registers, but it can only use like the bottom four or something like that.
Right.
The way that I was coloring something like that is that I would take that live range and then I'd have like 16 different like infinite spill like fixed register like pre-colored registers, and I would use those to like basically interfere against like the other 12, so that I would say that okay, since it interferes with the other 12, it can only use the bottom four. What I'm realizing now is that I could just color it with like the function for like what low degree means could just say like, hey, your number of registers isn't actually 16, it's 4. And then just like selection can handle that. So I don't have to have the extra ranges and the extra interferences between like pre-colored registers and like the normal registers. And it seems like you're doing that there.
Yes. If I'm
Yeah, because you don't seem to
pre-colored,
have like the pre-colored registers. You just like, I presume in like selection you just say like, oh, take the register mask and then just those are banned.
yes.
Gotcha.
It's when the register mask is set for every def and every use according to the allowed registers.
Mhm.
If you go down to 1, I claim you're pre-colored.
Okay.
If you go down to like 4, I don't claim pre-colored because you get these 4 different options.
Yeah.
So I only play this game if you're down to 1. Now there's a
Yeah.
heuristic game that says here where I say must def is true if you're down to these 2, and I'll pull both of them out of everybody else, and you're allowed to have either one of the 2, and no one else will have any of those 2. And
Mhm.
everyone else lost 2 registers to choose from, and you get 2 register choices, which is overkill in my head. So I do it for the 1, but not on the 2 case.
Makes sense. Yeah, I'm just thinking about like coloring like weirder register masks because the
Right. I'm this allocator is working on some very weird DSP like chip right now.
Mhm. Yeah, because if I were like coloring what would it be like pairs or something like that, I might color or I might only be able to
Yeah,
allocate every other like thing.
pairs have a different story to them. And there is a well understood heuristic for doing pairs, which complicates life, which I don't have implemented here.
Yeah.
But pairs do a game where you interfere pairwise and you have to ask the pairwise question. And you get a lot more interferences because the pairs get the 4x comment, get the oddballs, half sliders. So you want to
Yeah.
force even odds on the pairs. And then there's things you do for interfering and coloring and stuff. But you can, the C2 totally does pairs. It
Gotcha.
does complicate life. It's not a huge complication, but you have to kind of nitpicky your way through what it means to interfere.
Yeah, I haven't implemented pairs yet, but I basically like read through a bit of that only because like I imagine I will run into it, but I haven't like for x86. I don't care about like using the high registers or stuff like that for anything
Right,
useful. So like
right.
I just treat it all as like there's just RAX and
I
then like
don't
it
think
aliases
you'll
down.
hit pairs unless you start doing weird chips. There was a
There's a few
time,
weird chips I want to touch.
okay, there was a time when x86 you just had to do pairs.
Yeah,
So
the Z80
everyone
was the same way. Yeah,
everyone sorted out how to do pairs and they figured out the right way and blah blah blah. And then x86 kept getting more and more and more general, and suddenly, pairs are kind of a DSP chip of the past thing, and they happen. And if you're doing that kind of a chip, the deal.
yeah,
But if you're not, I don't think you need to do pairs.
yeah. I'm trying to. I've got like a few DSPs that I want to like poke at, and
Okay. Yeah. As soon as
yeah,
you say
they do in
DSP,
fact
that
have
you might want to do pairs. Yeah. It kind
yeah.
of depends. Yeah. Fine.
On an other comment, in terms of your like your machine like abstraction, basically,
Yeah.
mine looks about the same, except I represent like the register mask differently, and then yeah, this piece. Like I represent like getting the node constraints out differently, and then the other thing is oh yeah, and then I have like latency and what I call like the unit mask, which is like
Right.
just defines which like functional units you can use,
Functionally,
and that
yeah.
is for scheduling like
Yeah,
VLIWs.
I don't have any scheduling information in this setup right now, and it probably comes from my funny DSP I'm working on, but it's not here yet.
Yeah.
Okay,
Yeah, that's the other thing. Like half the DSPs that I've been looking through are like also VLIWs, so
right.
they have a bunch of funky like
Yeah,
functional unit stuff.
right. That you totally want to do. Yeah, I get it.
Yeah,
And then the other thing going on here is for x86, 64 bits and a long is probably not enough. So
yeah,
this format changes for x86 to
yeah,
allow me to
yeah. For me, I
return a
basically
larger thing.
also for me the mask itself is like bound to the class, so as long as the class never passes 64 registers, I'll be fine. But what instead I run into is like I can have certain masks, like the stack usually will cross it if I get enough if I get enough parameters or enough parameter passing or stuff like that.
This format has to include stack slots, so I have 64 allowed registers in this format, including spilling.
Yeah, makes sense.
Which turns out covers a lot of ground. Not many things have more than 64 things simultaneously live, but it depends on how many you eat up into your registers normally. So this will be too small for an x86 running generic giant programs.
Mhm.
Modest things that aren't doing giant DSP unrolling where you're expecting to have 32 things live at a time because you've unrolled that deep. Well, those guys will need more registers. Fine. So this is known that it's going to change.
Yeah, but yeah, I'm tweaking my like selection stuff now to like get rid of those funky pre-colored ranges, because the other thing is that they bump up the size of the interference graph by like a massive amount, even though they don't do much beyond just say like you can't use this register, and like I could just represent that in the like mask.
So in the bit set version, the max register number shows up in the bit set.
Mm-hmm.
And so you get the n squared effect for having larger bit sets.
Yeah.
When you go to the neighboring list, it's the count of neighbors. And those guys who are fixed in a single register have very few neighbors because I make all the other neighbors not use that register. And they only neighbor against people who are using the same fixed weird register. So they have very few neighbors. So the neighbor list is very short, very small.
Yeah.
At different times, I've played with having the bit sets in the bit set representation take like offsets where they have known pre-zero beginnings, because the bit sets, as you walk through the program, the bit sets are arguing with whoever's live, interfering with whoever's live at that point, and they kind of make a triangle, or they walk the diagonal with some smearing on either side. And I've triangulated, so it's just below the diagonal, but they smear just below the diagonal all the way down. And if you end up with these prefixes that are largely empty, and if there's a way to shortcut that in representation, that cuts straight into the n squared size.
Gotcha.
Somebody had a chat question, and now I can't find my chat button. Go back here, chat. What's chat say? Oh, Cameron says he's out. Okay, see you, Cameron. And that's building the interference graph and building liveness in the same time. It's walk all the blocks. Within each block, walk all the nodes backwards. I end up with a new set of live set in the temp. I start with copying the block out live into the temps. I do the temp, and then at the merge, I move the temp up into your parents. That's live. And then within each visit through the block, you set your interferences up, and you accumulate if you have to revisit a block because new things got live. So it's monotonic in that sense. So that's building the interference graph and building liveness to build the interference graph. And then there's coloring, and that'll be sort of the end, and probably we can walk away. Merge live out and all these other utilities are doing pretty obvious things with just moving bit sets around. So here's coloring. So coloring says I have an interference graph. I have some pretty prints turned off to help debug. I'm going to convert the array of, that's not very readable. Let's see here. How about there? Convert the array of bit sets into an adjacency matrix. That's what these loops are doing. There's build a set where you have a number of neighbor counts, n counts as neighbors, and then AFG is adjacency graph representation. And then I walk and I look at my bits and I go count and I count up so I know how big to make my adjacency list. So that's a visit. And then I go allocate, and then I walk again, setting bits in a square adjacency. And I basically copy the bit sets into an adjacency matrix that's packed. Then I have a simplify pass and an unstack on simplify. So this is standard graph coloring. Simplify is pull things out of the interference graph that are trivial, and then there's special hacks for when they're not trivial. When you're done, you reverse and you put trivial things back. Trivial guys always have more colors allowed, more registers than neighbors, so they guarantee to get a color. So when you pull out, you pull the trivial guys, the graph keeps simplifying, more and more things get trivial until you get to these cliques, these knot of registers of live ranges. They all touch each other, and now you're You can't color guaranteed. So you pull a risky guy out in order to make progress. That guy might not get a color. You don't know until you reverse. He may or he may not, depending if you can color his neighbors all the same color. Then they don't use so many different unique colors. And then the one guy who's at risk suddenly has room or not. So Aaron, you asked about randomness. The coloring stack essentially is random at this point. So coloring stack, it's a list of live ranges. It's broken up into these three parts according to the comment. The same as what I'm saying here. There's anything from the start of the stack to some stack pointer is known to be trivial and removed from the interference graph. Removed from the interference graph. And then from stack pointer to work pointer, it's trivial but not yet removed. And that could be empty if I'm out of trivial things. And then past the work pointer to the end is unknown. I don't know if I can color them or if they're trivial or not or nothing. So I just set the color stack to itself. It's just one live range number for every size. So that's a count. Color stack of I is I. Walk the live ranges and ask if you're trivial. If the number of neighbor counts is less than the number of bits in your register mask. If you are, you're going to color. So I swap you, and swap here is a utility that just takes an array into indices and swaps the members. And I swap them up front, and I move the work pointer. So I accumulate trivial guys between the start of the stack and the work pointer. So the S pointer is at the start, and then the work pointer is ahead with trivial in between, and then unknown is after. Once that's done, the real pass is here. Pull things in trivial order if possible. So from the start of the stack to the work pointer, it's all trivial. If you're not, I have to do something. Let's cover that in a second. If you are, I grab you and bump the stack pointer. Get a trivial live range, great. Again, if you were not trivial, I'd do something. Let's come back in a second. So now I've pulled a guy off the stack. He's probably trivial. I get his neighbors. Get the count of his neighbors, and I start walking all his neighbors. So this guy has some neighbors. Each neighbor has him in it because the matrix is square. Go find himself in the neighbor and yank it. And here I do this elegant trick that's I never saw before and it never got published, which I think counts a lot. And that I take the guy I'm pulling out of myself out of this guy's neighbor and I put him to the end of the list and I shrink this list by lowering the in counts. So there's a swap. I must be found. So find is just stupid walk the array linear scan find. And I swap you to the end count position, and I drop the end count by 1. So as I find people who are adjacent, I take them out, put them to the end, and I shrink. And the dude I'm removing is getting removed because he's trivial, but all his neighbors, they all shrink by 1. And as this repeats, people keep shrinking and shrinking and shrinking and shrinking, but the people they shrunk away from are left behind them in reverse stack order. And when I unwind, I can get them by simply, when I reinsert you into the graph, all I have to do is bump that tail pointer by 1, and I'll pick up the correct guy to reinsert. That makes life a lot simpler here. And then there is a test if you're exactly going trivial. So I'm removing the trivial guy. He has a bunch of neighbors. I went to a neighbor. I yanked myself out of the neighbor, and I went to the end. The neighbor shrank. He got one fewer neighbor he worried about because this guy's going to color, so he doesn't count for this guy's coloring issues. So this guy shrank to the point where he's now trivial. If he is, I put him on the stack in the trivial place. That is to say, I go find where he's in the color stack, and then I swap him ahead of the work pointer, bumping the work pointer by 1. So what's on the screen is the whole algorithm for doing the color stack in the one direction. Pull the trivial guys off, shrink all the live ranges as they go. If they become trivial, keep shrinking until you hit a fail point or not. If you're going to color, you're not going to hit a fail point. You're going to walk to the end and be done. And then I call pick risky, which picks a candidate which I'm likely to be able to color anyhow, but I have no guarantee I'll be able to color. And there's reasons why he's likely to be colorable. And that has to do with biased coloring and some color choice things going on. So I don't want to go into the heuristics on spilling here. There's lots and lots and lots of heuristics, but the main point here is that I don't know and no guarantee, but I have to pick somebody to make progress. So I yank somebody and say, let's see what happens and keep going. When that process ends, while the stack pointer rolls until it hits the end of the last max live range and I'm done, I now have this reverse stack of things that are reversed in order of where they were trivial. And now I need to unwind. And here's the unwind loop. And the unwind loop says reverse it. And everyone gets a color if they were trivial. And if they weren't, I'll find out when I get there. So I pull a guy off the end of the stack and I roll the stack pointing backwards, get his neighbors, get his live ranges, walk his neighbors. And everybody I walk, I go add one. I add myself back in because I now count for them. So I'm reinserting into the graph. So I'm adding the edge between me and a neighbor by just bumping the neighbor's list of edge counts because I stacked you that way. Then I grab the neighbor's register. He got a color, or he didn't. If he didn't get a color, then I have to spill and I don't count. But if he got a color, then I take it off of my list of color choices because my neighbor who I interfere with, we're alive at the same time. I can't use the register color he got. I have to pick my own. If I ran out, I failed and I spilled. And I have a coloring fail and I have to go split the graph. But if I didn't run out, then I'm going to pick somebody. I pick the lowest guy as the default choice. But then I'll do biased coloring to try and make life easier for people who weren't guaranteed a color and see if I can arrange that color choice I pick. I have all things in my register mask as choices. See if I pick a guy who I can get rid of a spill elsewhere is what it amounts to. And then I assign the register. And I repeat unwinding the stacks as you go. And if I don't hit the fail point, we're done. And if I hit the fail point, we have to get into split logic. And that's a giant wad of all kinds of things. So then there's a bunch of heuristics and a bunch of pretty printing. And you know that's sort of the big picture here. Let's go back up. So not counting split, that's the big picture. Run through rounds in the register allocator, pride and color, split if you failed, sort if you failed too hard, and then a coloring round is build your live ranges, collect all your register masks, union up all the people who are part of the same live range due to two address ops or due to feed functions, and then build an interference graph, which requires liveness along the way, and collect who tangles with who, and then go to coloring where you take the people who are trivial and you throw them out of the graph, and the graph keeps shrinking and shrinking and shrinking until you get these knots that you can't guarantee color and throw somebody out anyhow and run the graph to empty, and then you unwind and assign a color as you go. And if you get it, you got it and you're done. If you don't, now you're into splitting. And then splitting is just a giant wad of heuristics. Okay.
Cool.
Yeah, your brain's all fried now. It's just like go on or splitting or not.
I'd love to see splitting because
because you're
I'm
here
also
and
doing it, and so
all about it. Yeah. Somebody else was going to say something. It's probably Theodore saying go do splitting.
No. I think I've got some of it, but I will definitely rewatch when I get more information about register allocation and graph coloring and stuff.
Yeah, this is not set up where I can demo because I'm intending to have this in simple and I don't have the pre-pieces there. I've been using this setup on allocator for Derek's wild-ass chip, but it's basically a clone of C2, more or less. A few things changed to make it a little easier. It's written in Java, not in C, and all that kind of stuff, but it's essentially a clone of C2. Okay, well, let's look at split. So split has this some list of heuristics. This is not the complete list because I've fiddled some more over time. But basically, I know that you're in trouble. You have a list of the in trouble guys, and I have to decide what to do with them. And it can be done while you take a troubled live range, a failing live range, and visit every place it shows up in the program and do something about it once per live range. That's a simple, easy to understand way to start thinking about splitting. So I can make some choices about a live range. Hey, this live range is going to be split this way, and that live range is going to be split that way. And then that's slow and that you visit the whole program once for every splitting live range. So instead, you do this loop fusion thing where every live range is visited in one pass of the whole program. But then when I arrive at a point where I'm dealing with a particular live range, I have to decide again, what the hell am I doing with this live range? And how am I splitting it? And my choices are things like you're an easy constant. Rematerialize is the key word here. You're a constant of some kind, some cheap op that's easier to spill, to recreate than to spill. Sorry, recreate than spill. These guys, I'm probably going to split at every point, except maybe outside of loops. And that means the original def will go dead. And I'm just going to remove the original def. Common case is I have a 0. I've shoved a 0 in a register. Everyone CSC the 0 together. I have zeros for floats. I have zeros for ints. The ints and the floats conflict. They can't be in the same registers. I need to at least split you to a float 0 and an int 0. But I probably want to split you as a fresh 0 outside of every loop, or I don't know what. It could be in front of other ops. Who knows? But I'm going to be splitting that 0 a bunch of ways. And I might have other constants that are long lived that I'm going to be splitting. Well, by splitting, I mean I'm going to be making a new copy at every use point, and there won't be a shared def anymore. So that's one technique. There's the obvious technique where at the def site, and there may be many defs because the live ranges have many defs and many uses. At every def, we all spill down to a stack. Every use, we load it back up. This is the expensive version of things that guaranteed works because every live range that's left over, you get these little tiny live ranges that are one instruction long. There's the original def, and now a split op, and then there's a new live range after the split, which spilled to the stack. So under that model, all live ranges become chopped into tiny one instruction op live ranges, and there's a big old shared live range for splitting, which probably ends up on the stack. That one's expensive, especially in hot loops, and you'll see a lot of that when heuristics fail weirdly and you split where you're like, no, you should have not done that, whatever, it's like suck. So then there's a gradual version of this where I say, I'm going to look at live ranges in loops outside in. And I'm going to say, if I'm going to split you and you're used in this loop nest, I'm going to take all the defs that are outside the loop and split them at the loop header, and all the uses that are past the loop and lift them after the loop. But I'll try to get that live range not in a register in the loop. And then in the loop body, I have more registers, and I quit spilling in the loop. So this is commonly a thing that'll happen if, for instance, call or call save registers. You come in, your register being passed in. A call or call save register is one that the calling convention says you have to not destroy. So I def R15 on entry and I use it on exit. I'm not destroying R15. I have to preserve it. It's one def, one use, whole program. I might as well split it up here and split it down here. It goes to the stack. That's your call prologue being built by the register allocator without a call prologue. So this kind of allocator builds its own prologue. And because it can be smart about early exits and it can be smart about loops and it can be smart about profiling and hotness of the code, you get better spills than a standard dumb prologue that just says spill I ran out, so spill the things that I have to call save and call or save. So that's a heuristic that runs around. There's the split by loops, and if I split and I'm still in trouble, then I'll split again around the inner loops until I run out. Once I'm in an inner loop and I'm still in trouble, I'll start splitting it hard, where I say every def and every use, there's some conflict going on I can't resolve. So you get this set of heuristics that don't necessarily all apply in the first pass, but they start to apply at different related passes. So I'm kind of going to go talk through kind of the heuristics running around, but that they vary and when they apply and stuff. It's like difficult to see without a concrete example, which I'm not ready to show a concrete example. So just for flavor. So walk all blocks, walk all nodes within a block, forward pass over the whole program. Grab a node. If it's not a spill, don't bother. This should say if spill, not spill, continue. Walk the node, walk this def. Is the def spilling? No? Well, then don't bother. Or the def is spilling. Am I going to have some kind of progress or not here because this def is, for instance, a spill op immediately in front of the use. I have some other conflict running around. The use is in RCX. The def is a spill, can be in anything, but he's got to load into RCX. Somebody else wants RCX. I can't have it. I can't make any progress by spilling here. I have to spill the other dude. Well, he should also be spilling. The other guy is also spilling, the other guy who wants RCX. But spilling again in front of a spill makes no progress, so don't bother. So immediately comes this conflict of, I have a heuristic here, I have another heuristic over here, they're fighting each other. I have to spill this one, I have to spill that one, but this one won't make progress, so I don't want to actually do something. Kind of thing going on. Grab some loop depth. Find the deepest point that you're deft. Find the points where you're used. There's some heuristic on this use. And the question is, are you deft outside or inside? Do I want to leave you deft outside and then use you inside? If you can live in the loop, that's nice. I mean, you can live without spilling in the loop. Otherwise, I need to load it up, spill it outside the loop and load it up inside the loop. It'd be nice if I didn't spill you. So should split here is like, am I forced to split? Because, for instance, I got no register choices. I have a hard conflict. I haven't made enough progress recently. I'm out of loop nesting depths to work my way into. I just have to split here. If I do, I'm going to make a split. The splits come in two flavors. I copied from a prior guy with a spill copy, a copy op, a load or store or reg move. Or I'm rematerialized, which is probably make a constant, but maybe it's a funny other thing. There are other things you might rematerialize. And then where do I put it? I put it, in this case, immediately right in front of the use. And I set the use's input def to the split instead of to the prior op. But the split that I made points to the prior def. So it's a split. I have a use pointing up to a def, and I put a split in the middle, and the split points up, and the use points to the split, kind of thing. Okay. So that's, I must split you because I have no choice. You must be split to make any progress. Then there's the, oh, I'm going to split you because there's a loop thing going on and you're in or out of a loop and I'm trying to figure out whether I should split you and where. And then this is the def and the use are here, or the use is out of the loop below it and the def is in the loop. And can I, if I must split you, where do I split you and the like? So figure out which of the two directions you're going, and then set a split somewhere. It's at the use, but the other side is either in or out of a loop, and I'm either in or out of a loop, and I'm trying to decide where to put the split instruction. So the use is where the use is at, but where's the split go? So that's the standard. I walked all your inputs and split them all. Then I'm going to do your defs. So you're a def, and you're going to produce a value going down, and you're an is clone. Then there is a you're an immediate constant, and I'm just going to make the new constant at every point. Or you're a popular constant, where I want to say, hey, you loaded a 0 and you use 0 27 places for ints and 35 for floats, and maybe I want to split it into the ints and floats first, then maybe I'll split the ints from ints and another pass or not, or whatever. So there's this popular constant notion. And then there's another notion which says, still in the I'm an is clone, I'm going to go ahead and put you a copy of you right in front of the use. So I have a use of an immediate value, maybe a 0. I'm going to put a low immediate 0 right here. And also I want to get rid of the original def because I'm going to put all uses are all just going to have an immediate def. They're just going to, that original def will go dead. Otherwise, it's a more standard split where I say I have a node and he's a def and he has some uses, and I'm going to put a def right after the split right after the def. So I produce a value and it just goes to the stack. You might be defing multiple values. I'm a div mod. I have a def for the div and a def for the mod, and one's an RCX and one's an RDX or whatever the hell they are. and I need to split one or the other or both, and then I split them down to the stack, or maybe RDX immediately goes into a call and it's in the correct register and I'm all happy and I don't have to split or whatever. So that's the choice of walk all the things and do the same question for all my multiple outputs. So that's the high level of split thing. It's walk everybody one pass and make a decision for every use and every def. What am I doing here? And then there's a million little helper functions. And the helper functions have all these flavors of, hey, do split def sys. Should I split? If so, go get a split op from the architecture and make one, however that makes a split op, and insert it. And then the insert split is like, I put you at the where in the block ahead of the use or behind the def, except that if you're being at the head of a block and the block has fee functions, you have to be after the fee function. So insert split actually walks the block looking for insertion points. Here's a no progress check. Decide if I have multiple users, I must make progress. You're some kind of reason that you don't produce a value at region. I'm hearing the wrong point altogether. Rematerializable. He's going to progress because I'm going to split you off or not. Whatever. There's a bunch of heuristics for that. Should split def is like I'm killing a register, but I'm not spilling it. This is an instruction. It's a div mod. It kills RCX. And it sets the remainder in RDX. And I want the remainder, but I don't care about the div, but I have to kill RCX anyhow. So that's what that one is saying. Then hard split is like, give up on all the fancy shit and every def and every use, just split. If you're hard conflicted, you're down to one register. You must split here because you need that register. If you're in the same loop nest, the min and the max loop nest are the same. I'm not doing a loop depth-based thing. Otherwise, maybe I can do something around loop nesting and I can spill outside of loops and not inside. And so don't split it yet. Should move. Let's see here. Oh, yeah. Yeah, this is like, should I make a rematerialized op or should I reuse an existing one? And it got all kind of fancy stuff going on here, where I'm counting ops and I'm trying to decide that you will or you won't, or it's profitable or not. And I went to a profitability heuristic, which returns me a score instead of a yes/no Boolean. Here's the use side version of the hard split test, where I ask questions like, hey, you're rematerializable, you're clonable. We'll go ask the question the other way. Otherwise, hard split is fail always. Or if you just want use, you must get your use, get it. Or I'm going to ask questions about put a constant here or not put a constant here. Single def, single use, same block. Might as well split it right now. If I failed already, if you're a single def, as you have only one defining point, you have one use, and you're in the same block, and you still didn't color, unless you're fucking adjacent, there's no progress to be made by being fancy here. If you didn't color, there's something hard bad going on. Split it. Be done. Oh, I'm already a spill op. Don't spill a spill. Def is a spill. Oh, he didn't make progress, so the use has to spill. Yes. Otherwise, I'm down to the loop nesting depth thing. If the def and the use are different blocks, there's a block. There's a loop, and the def's outside and the use is inside, or the def's in, the use is out. I might want to do something clever on the loop borders, and so on and so forth. So anyhow, the heuristics go on and on and on and on and on and on and on. There is a post color pass, which just looks for things I can locally get the same color on the spill code. Your spill, I get your def and your use. They're the same. I colored you the same. Biased coloring for the win. Okay, get rid of the guy. It's a spill op that spills RCX to RCX. I don't need it no more. Get rid of it. And so on. So that's a fast run through what spilling looks like. I think the main takeaway for spilling or splitting here is that it is a heuristic problem. You're looking for common, interesting scenarios that you can cover. You must guaranteed make progress. You do not want to hard split and force rapid progress because you will get a bad set of splits that you will not be able to color away. They will not be biased coloring to disappear, and you'll get a crappy, correct, but crappy allocation. So you have to just gradually creep in on a correct allocation. You sneak up on it. And while you're sneaking up on it, you have to keep making progress. And that's one tension. And you have to not get on it too fast or you get too many spills. And that's the other tension. And now my voice is going, and so I'm going to be done.
For the most part,
Then what
everything
would
but
make
my
sense?
splitting stuff. Oh, what's up?
For the most part, what?
For the most part, everything but the splitting stuff and the thing I mentioned about like register mass, which I just tweaked now because so I get a lot of stack live ranges because technically the what's it called? If I put an array on the stack, that becomes like 10,000 like live ranges or something stupid like that. It does break on the Chitin or like Briggsy one, but now that I've done the register mass thing, it shouldn't because they shouldn't count as live ranges now. Like the fixed ranges of like stuff that I've reserved on the stack shouldn't count as live ranges anymore.
Right.
The only reason I kept them there is because like they're logically taking up those slots, but like they're not like
Oh, I see.
they don't.
No, I always ran them as separate. Like I do this stack
Yeah.
coloring thing here. I have all these live range numbers for the stack. Then you got some stuff put on the stack because C code says, hey, stack allocation, stack deallocation.
Yeah.
Okay. That's not anything to do with coloring at all. That's just
Oh,
some
sure.
space I put on the
So
stack.
I'm going to be coloring those actually, but like that's going to be like a separate coloring pass because
I
those are going to
see.
be colored by
Oh,
like
you have
assignment.
C code that's making and dropping 4-element arrays and put some arrays
Yes.
on the stack and then getting rid of it, putting an
Yeah.
array, get rid of it, and you want to recycle that.
Yeah, exactly. So there's like a mixture. So I want to do like a first pass of like, okay, these can be colored and then compact that so that I can get a bunch of nicely compacted like stack items that are like explicitly addressed. And then
Right.
those become a chunk of the like stack slots. And then the
Yeah.
rest of it is like the spills, those get colored as like a
Right.
separate thing.
Right.
But like a coloring, so currently I like do like a very dumb coloring where or I do a very dumb thing with those like C live ranges where I just put them on the stack and they just take up a bunch of slots and
I
like
yeah, I didn't understand, but now I get where you're coming from. That makes sense to
yeah.
me. And splitting them out makes sense because you probably have very few of them and they have odd sizes.
Yes.
Whereas the normal live ranges for registers like you have hundreds to thousands.
Exactly. Yeah. For the most part, like all the like stack slots are going to be like about the same size. They're either going to be like 8 or maybe even 16 sometimes, but usually they're going to be 8.
Right. Right. Yeah.
But yeah, so I do the first pass, which is like on the names effectively. So like the allocations, figure out like, oh, do these things interfere? If this thing interferes with like these things, then it can't be allocated with them. But like maybe I can do like this thing is like 4 64-bit values that could actually be like aliasing on top of like 4 other register or other stack slots that are used somewhere else.
So as soon as you have multi-word things that you're trying to register allocate, you get the multi-word register allocation like pairs, but it's more you have to use the
Yeah.
general version, not even the pair version.
So at that point, I'm just considering dropping to like linear scan because it's not like I don't care enough.
Right. Right. You're not going to
Yeah,
get a huge
I
A.
just really need to like recycle some stack slots. I don't need to recycle all of them or anything that serious because the main thing is just like, for instance, in C, you might open a scope and close the scope, and people will do this all the time where they're like, open a scope, make an allocation in there, and then close the scope, and they kind of expect it to like recycle the memory.
Right.
Because you kind of expect the stack slots to be like emptied out, but for like LLVM or for GCC or for any of the modern compilers, they don't like they usually erase the scopes during the IR. What you do is you usually like bring them back in by having like annotations that say like the lifetime of the stack slot is ended, which means that it can be recycled now, and then so that just gets fed into like some stack coloring thing.
Right. I claim that's a reasonable choice for a linear scan.
Yeah.
Like graph coloring works great for very complicated graphs. So complicated control flow graph, complicated lifetime management things.
Mhm.
And everybody counts the same as a word, whatever word is.
Yeah.
As soon as you have multi-words, the graph calling conflicts for the interference graph get very large, and the
Mhm.
set of gains you're going to get, it shrinks. Yeah. You go linear scan there. That sounds reasonable to me.
Yeah, because like worst case, I just happen to like not have as small of a stack. It's like it's not gonna do anything like weird splitting or anything like that. Or
Right. The penalty for extra stack is a lot cheaper than the penalty for spilling to the stack.
Yeah.
Yeah.
But you're not fitting that whole array into registers at one time anyway. It's not like the array is
No.
three
So they
long,
wouldn't be
is it?
colored as registers. They're like like stack space basically.
Yeah, yeah. If you can lift it into registers, that's an IR thing, and the
Yes.
optimizer should have done it already and lifted it. The
Yeah.
escape analysis got it into registers.
Yeah, exactly. So there's like if I've got like stack slots that can fit into registers and that do get used as registers like that, then those will be fine. But there's sometimes that I might have an allocation that gets fed to another function, for instance, like oh somebody makes like this little like stack array, feeds it to another function. I can't get rid of the pointer there, so
Yeah.
because of that, I have to
Right.
color it. But if that thing doesn't alias with a different stack slot in another place in the function, I could just recycle the same stack slot.
Right. Right.
And in C, usually you get those because of scopes. When you open and close scopes, you open a scope that's like its own lifetimes. All those allocations die by the end of the scope.
And performance should not be super hot there because you didn't inline that call.
Yes.
If you have performance problems there, the first issue is fix the failed inline.
Yeah.
Yeah, fine.
Yeah. Fuzzer generates a bunch of massive arrays. I think I've got like a few, like a 4 kilobyte and like 8 kilobyte like arrays in there, and it looks very funny because it says that it's coloring a bunch of stack slots that are like all fixed.
Mm-hmm.
But
Right.
it doesn't really like they're all fixed, so like it doesn't really color them.
So in the land of C2, I don't have this problem because it's Java.
Yeah.
If escape analysis worked, you get hoisting the registers, and then I don't still have a stack allocation thing. And there have been some attempts to stack allocate things outside of what I did at Azul. What I did at Azul is very carefully limited to you acted as if you were heap-like, but you tracked lifetime and saw that you were stack-like. But I also had heuristics that said, oh, you're stack allocating a 20 megabyte array. Okay, I can't put you on the stack. I don't have a 20 megabyte stack. So there are issues there as well. I had a lot of those. It can be stack allocated, but I don't want the stack allocated.
Yeah, it makes sense.
I do wonder how often a compiler is in a better position to make a decision as to what to stack allocate than the developer is.
I claim the stuff I did at Azul did a really good job. Like if you're not doing a generic GC already, like the Azul GC is really good. So if you're not doing a generic GC or you have bandwidth issues, like Azul hardware had enormous bandwidth for the time, just enormous, but tiny caches. So you could always run allocations and he would just burn bandwidth, which you had lots of. You go to an x86, you have giant caches and tiny bandwidth. And so you'd rather recycle rather than continuously allocating. Okay. Right. That one I'll have to handle in a minute. That's my home insurance lady who does fire insurance, and it's California, and fire insurance is an issue. I will call her back after CCC here. So the cost for SBA, stack-based allocation on Azul didn't pay off versus the great allocator. But on an x86, that math might reverse, and you might be better off with a good stack escape detection, stack allocation strategy, and less allocations that go to the general heap and force a bump pointer allocator to run you out of bandwidth.
Yeah. While it's true that like the programmer could be able to tell which one is like better, like whether or not using the stack or the heap. If you're in like Java, the programmer can't tell the compiler that. So because of that, if you can get even some things going on the stack, then like that's already a win. As long as they're not like huge and will blow out the stack.
Said everybody went to the stack until they failed out, and then you rapidly honed in on. So you asked, is it possible the compiler? Well, the runtime could rapidly deduce, not the compiler. The runtime could rapidly deduce what allocation sites could be stack allocated reliably. That was one of the big outputs of the stack allocation work I did at Azul. Given that, you could go tell the compiler to inline up to that point, and things would be stack allocated. Statistically speaking, the vast majority of the time, you rapidly honed in on the correct allocation depth, inlining depth to get the allocation to stay within the compilation unit, so you were stack allocated. That was highly successful. Now, having said that, what was the count? Well, in big, busy app servers, a couple different guys, I could get around 60 to 70% of everything stack allocated. which I thought was pretty damn good for a giant multi-threaded, heavily multi-threaded app. On an x86, those would all become cache hits versus memory bandwidth, which I think would be a big win. Azul didn't have enough cache to support the kinds of sizes things I needed to stack allocate in order to stay allocated in the stack. I had to allocate too much, it wouldn't fit in the cache. So he lost the cache benefit. x86 hardware might change. You could get a lot, and it's not the compiler doing escape analysis. It's the runtime doing escape detection and informing the compiler, hey, this call site escapes at depths 1, 2, 3, and not at depth 4. So if you inline up to depth 4, you got a builder, you get the builder layers. He won't escape. And the flip of that is the compiler could now know that if he attempted an expensive escape detection, it was statistically likely to win because it had never lost yet. So there was a hint you could tell the compiler as well. This thing both has never yet escaped, and maybe an escape detection would work nicely here. So there is things to be done there. I think that would be the right way to go with the whole how to escape the world thing, or at least in my head, it's a pending unanswered question that seems to me that we could get a lot of interesting auto memory reclamation stories sorted out without any annotations, without any rusty annotations by merging.
Well, but then with this approach, if you're just guiding the inlining, you are limited with how much you're willing to inline.
C2 was always very aggressive, willing to inline shit tons. So that was rarely the issue.
Oh, we are doing it much more aggressively now, and we run into situations where I would love to inline further so as to make something unescaping, but it's just insane. Like you don't want compilations of this size.
Yeah. So the other piece of the escape detection thing is it says it will stay stack local, and maybe you don't want to inline enough. You could still allocate it in a higher stack frame. So that's one of the things I did with stack-based allocation. I counted up what stack frame point it would not escape at, or went to the heap, and I would inform the compilers. And the compilers
count how? How do you determine
you look backwards. Well, at the time that an escape happened, it was layer by layer. So I've made a bunch of calls, and I come down to here, and unbeknownst to the runtime, it's a bunch of factories that are stupid, and then there's some real work being done, and then I got an allocation. So the allocation happened maybe in the interpreter at some point, happened in an early JITted version of things, whatever. So an allocation happens here. Then I store it into some other place that forced an escape, and I looked at where I stored it to. I probably returned it, and then I went up a layer. So I go to the allocation site, and I say, you, Mr. Allocation Site, you escape up one layer.
Wait, so does it mean that you intercept all the stores of that pointer?
Yes, it's a store barrier.
Okay, so
same as it's an Azul hardware. You get store barriers for free. The x86 version store barrier wouldn't be that much harder. The store barrier was literally range check on the address versus your stack pointer and jump to a fail. So it's a one clock, highly predictable, doesn't fail thing. Doesn't need an extra register.
Is the where is the allocation happens? Is it in the heap, or it's on the stack, or in some special region?
Well, it's on the stack. The early versions I did, I literally had it on the stack, and I had to preserve space that ran out of, and then I had to make a side array. Later versions, I just said it's a stack-shaped side array that could be chunks from the heap if I cared, but I'm thinking it's stacked because I want the locality of reference. So it doesn't matter if I threw it in the heap or not. If I'm declaring it stack and has stack lifetime, I get stack lifetime in my caches. That's my cache win. Okay. And then I have lifetime management for reclaiming the storage. I'll just recycle the shit in the heap. That was another version. And of course, I have the VM, so I don't have to be type safe from the Java point of view here. I can reshape the same memory in the heap to other kinds of Java object types.
Yeah, then you piggyback on the store barrier, and you check if this store will be escaping.
Right.
Okay.
Right. Yeah, yeah. And then, like I said, the usual story is at some point, so it was strongly normalizing. Each allocation site went up some count of layers and then quit escaping after that. And you just had to count the layers. And the next time you came to that allocation site, you went up that many layers to allocate it. And if you were the interpreter, you just counted interpreter frames. And you had a slot of chunked memory for each frame that you would put the stuff in for that frame. And then if you're the JIT, he just merged them all together and counted the space up and did it,
Oh,
the
wait.
obvious way with the JIT.
You are saying that you would effectively sync the allocation to the point where escape happens.
Yeah. The
Uh,
first cut would fail badly, and I would escape it the hard way where I walked the stack. It's still thread local. I'd walk my thread stack and adjust the pointers and move it. The later
Mhm.
cuts would know, oh, I want this 3 layers up. And if so, still assuming interpreter. So when I make an interpreter frame, I make a side array of size 0 to begin with that's going to hold frame things. And then when I escaped and I moved you up a frame, I adjusted my pointers to say, you're a stack pointer for that frame. And I put you over here and I have some cheap ass check that works in the interpreter. The interpreter escape detection was a little more expensive. It wasn't so cheap as the JITted one because I had to know frame by frame by frame. The JITted one did a thread local or not kind of thing. And then he bailed out to the interpreter. And like I said, these things normalize pretty quickly. Then the JIT would get it right.
Did I understand correctly that at some point you know the depth at which an allocation escapes, and then you
Yeah.
are doing something with the yeah, I think this part I didn't get yet.
I have a paper I'm going to get the link to, and I'll throw it in the doc. If I could go find the paper, this is one of these things. Uh, Dropbox, you're not helping. It's either presentations or papers. It's probably presentations. I did a write-up at Azul. Yeah, here we go. This one or this one. Here, this one. Okay. This is SBA round 3, which is me doing, what do you call it, a history, a write-up. Let me copy Dropbox link, find the thing. Where is the links? Bam, pasted in the links. Okay, there's a Dropbox link. So this will be, I'll write some here. SBA experience paper.
Yep, got it.
Let me do this. Let me hit the share. Share, boom, something. So it's a write-up. It says things. It talks about what I attempted and what I didn't. There's some hardware support. Like I said, the in support that you would put on an x86 wouldn't be bad. Azul got it for free out of the hardware. There was escape events. The escape events would move objects. You got thread local GCs to move an object. It's your stack only, so it was cheaper, especially on the Azul hardware, because I could do things with the pointers math to make it a little easier. But you do crawled your stack and you move things. So there was a first round, a second round, a third round that got progressively better and handled progressively more issues. I'm trying to find where I would say things. Allocation depth hints are discovered by trial and error. They're initially set to 0. On escape, the hint is bumped. The escape came per allocation site. In the interpreter, I had a little side thing that was 1 per allocation bytecode. It was just a side array next to the interpreter's bytecodes that was for this bytecode. Here's the hint. You didn't have very many hints, so you didn't have any allocations in a standard interpreter, so you didn't have many hints, so it wasn't very big. And the secret here is strongly normalizing. In other words, allocation hints are strongly normalizing. Depth hints. After few escapes, we home in on the ideal hint depth. So allocation sites get named. That's your or way to track backwards from an escape pointer to an allocation where it came from, which meant that stack local objects had a pre-word that contained hint data. So if you stack allocated an object and you didn't know it was going to escape or not, you kept a hint around. That way it just put it in the word in front of the pointer that said, here's where I got allocated from. And then I have this, I said Pascal style display. It's just an interpreter stack, but it's a stack of pointers to these side structures that contained the objects after they got moved. And then discussion about success and failures of round one. We never got all the corner cases out, and pre-made frames got considerably large. We got bad pathological escape cases where we had giant escape rates that were constantly escaping, and things like that were going on. So there was a round two. I did a bunch of things with locality. I did a bunch of things with the simplifying. I did a bunch of things with pathological cases I didn't quite get all. I discussed it in some depth here. This one was one where I rapidly knew how big to make a frame for the JIT. So the JIT would just bump the stack and he would make it big enough to take the escapes that were coming into him. And they wouldn't be escaped, they'd be directly allocated in his frame. So you had a JITted frame, calling a JITted frame, calling a JITted frame in the hot, fast, good case. This JITted frame, JITted code would have a stack frame that was big enough to take things that had to be allocated in this frame. You said, I don't want to inline this much, it's too much. Okay, you didn't. This guy didn't inline the call down to the next guy down here, but this guy allocated in his frame.
Oh, wait, so the Kali allocated in the caller frame.
Yeah, and some in-depth up in caller frame. So you had a Pascal, you could go say, oh, based on hints, I need to go up 2 frames or 3 frames. So
Wait,
I go to my Pascal
what,
display, -2, that's that guy's frame.
what is the point of this? Is it for wait, is if an object truly escaped, you need it in the heap, so nowhere around.
No,
right?
if it went to total heap escape, I gave it up and went to the heap, and that allocation site got marked, just allocate it in the heap. So this was allocation sites that were marked still as thread local, but escaping up some number of frames from the Java architected stack frame point of view. So the assumption was you weren't relative to the main where you called in, you're relative from the allocation site with the base of a factory, you went up.
Okay. So you are talking about the situation where this object is returned up multiple frames. It's not that you pass it down to. Okay.
No,
okay.
Passed up multiple frames. Yeah.
Got it. Okay, makes sense now.
Okay. And then of course up here where it got allocated, somebody come up here and passed it down and back and passed it down and back and passed it down, but it never escaped again. He's too high. So if I knew you weren't going to escape at this layer, the guys down here didn't have to escape check this pointer. Okay. So successes and failures, and then there was a round 3, which did a few more things and got life a lot simpler. And I gave up on doing certain kinds of GC things. I could get thread local storage areas that were known to be thread local, but quite large. And I needed to do a generational GC on them, for instance. You know, you're a 1-thread program. You just start a thread and it does something big and complicated. Well, nothing escapes the 1 thread. The entire program allocation lives in 1 thread. Okay, it allocated a bunch of shit and wants to do thread local GCs on it, which it can do. Okay, thread local GCs are generally cheaper than generic heap GCs, but the generic GC in Azul was completely concurrent background and multi-core. So if I got a large enough set of things to go GC, I wanted the background GC to go work my thread local storage. But the background GC wasn't thread local storage aware, so he could move things or relocate or whatever he's going to do that wouldn't be managing within my stack mindset, within my stack invariance. So I couldn't use the good GC for this giant heap thing. And it was like, at some point I needed to give it up and say, you had long lifetime. The goal of the stack allocation was to say, I can recycle lifetime things. But if you have long lifetime, that's not, there was no goal there to make it. I didn't recycle you in that sense. And I don't need you on a stack now. I can throw you in the heap. And if you're common, you'll be in my cache. But it's the goal of the stack local was to say, I bumped you and then I unbumped. And then I rebumped in the same space and I unbumped and I rebumped and I unbumped. Just like we were talking with Yasser just a minute ago when he's making his little stacked frame arrays and then reclaiming that storage. That's the goal. If it turns out you have a lifetime that's, I made it, it's thread local, and it lives forever, there's not unbumping. No point to it. So take the link, read it. A lot of fun stuff in here. A lot of things that, like I said, were really cool, worked out well, and things that were kind of surprising didn't work out. But one of the main things for the whole where it worked and where it didn't was the trade-off between bandwidth and cache on Azul is basically reversed versus an x86. X86s are drowning in cache and are rapidly or routinely considered low bandwidth because like 2 to 4 cores can run you out of bandwidth. But I got a 20-core machine from 5 years ago on my desktop right now. I can run it out of bandwidth in a heartbeat. So, do that billion row challenge. I'm ranting.
Yeah, I assume it was all in prototype stages because nothing of that left traces in the product to this day.
It lived on in all kinds of prototype space I had where I was trying to get it good enough that it was worth turning on in the main production, and it never quite made it. It was close. End of round 3, I had other things going on in my life, and I ran out of emotional energy, and I ran out of lifetime, and I ran out of whatever, and decided I wasn't going to beat the Azul GC on the Azul hardware, and I walked away from it. So then this write-up came around as let me remember what I learned here. And one of the things I learned was allocation sites are typically highly normalizing how far they escape. That's a useful fact. That can be turned into a later allocation strategy. They are the escape detection can be made cheap to test and rare to fail. So you can do escape detection reliably.
So for detecting the depth, were you using the max of all the escapes you encountered? That's why it was normalizing?
Yeah. Mm-hmm. Yeah, there could be paths. And one of the things that did come around was that when I inlined at an earlier compilation of C1, I would get private inline paths for different allocation sites. Those could have different hints. They would have different hints and say different things about where to go. So as long as I kept uniquifying the allocation, like cloning the bytecode for the new and getting unique hints for every cloned version of that bytecode, I could get unique hints and they would be different, and that was helpful.
Mm-hmm.
So I don't believe I got to where I took a C2 set of hints and used it in a later C2 compile, but C2 would inline more and then get more different hints at the different inline sites.
Yeah, what we do now, we rely on static analysis also for inlining. Like we go long ways analyzing down the call graph.
Right.
If we can see that we can make allocation unescaped in some in some cluster of inlining decisions, we would inline the whole cluster.
Okay. So one of the things that maybe you found this one out too is that I would have escapes only happen if you threw an exception. So the common case was you didn't throw an exception, no escape. And because I could escape you to the stack, if you threw a rare exception, I might have to crawl the stack, find all these pointers, and move the object to the heap. But I could do that. So I could live with objects that would only fail their escape under these various rare conditions. I say escape for throw an exception. That was a common one I saw for when it was failing.
But I think
rare condition.
This exception throwing code path will likely be replaced with uncommon trap with just the optimization.
Right, but then it goes to the interpreter who has no clue and says, all these sites I'm expecting to be on the heap already. because the allocation said they would have been on the heap.
So
Like,
we don't do this in the procedurally, but for local stuff, both OpenJDK and Zing has a way to describe how to allocate some of the values for the deopt state.
yes.
So that
Yeah, I remember that was going on before I left Sun.
Mhm.
But
Well,
I didn't get very far before I left Sun, but I knew it was coming on afterwards.
So it didn't exist in Zing up until, I don't know, 5-7 years ago.
I had it in this work at Azul, but but it didn't
Yeah,
hit the mainstream.
it exists. It existed in OpenJDK. We did different implementation of this, and we basically have a DSL for deopt handler. We can
Right.
describe things like you can allocate, you can I don't know, do subloads, you can I don't know, take locks, release locks. So it basically you can sync various operations into this DSL if you don't like them on the like in the compiled code in the fast path.
Right. Well, not in the fast path for me. Well, for what I had at Sun, when I would go to a deopt path, that the fast path was fast. The deopt took me where I had code that would do unlock locks and spill this or generate constants or whatever's going to do. It did some things.
So if you're talking about explicit uncommon trap, yeah, it's not on the fast path. But you'll also have deopt states on like GC polls in loops or like on hot call sites.
Yeah,
So
right.
these are on the fast path, and you want to sync
right.
some
I
operations.
claim when I was at Sun, I made those behave as if, when did I do that? I did that work some point. Wonder if I did it at Azul. I did this work at some point where if the deopt had a lot of fancy shit and they had in the middle of a hot loop, I had a deopt point, had one somewhere, and rolling jam, he's still fairly hot. I put a path off to the side and said, low frequency, expensive branch. If you're deopting here, you first pretend like you took a jump over there. From the compiler's point of view, it was a low frequency, rarely taken branch. And then that was a deopt and he just spilled and he rematerialized and he screwed around over there. Although I didn't make new objects from whole cloth. I didn't recover in registered objects that now needed a heap form.
Would you do this for just regular uninlined calls that are safe points for you?
No, I think I was only doing that for shape points and loops.
Okay, well, explicit safe points, yeah, I see you can have a control flow where.
Yeah. My theory on calls was if that was a performance problem, fix the inlining.
Well, we had this stance for a while, for like multiple years.
Right, you told me.
Until we ran into the limits of inlining, so we actually had to go and improve our code gen around save points and
right, yeah,
do other things.
Okay. Yeah, well, if you're doing if you're allowing the call to exist somewhere where it's hot enough that you care and you want to do these other things, then yeah, then it makes a lot of sense to do what you just said. I have this DSL for describing state that I can rematerialize slowly, but I don't want to have code for it lying around.
Mm-hmm.
Yeah, I could have done it for calls though. I could have said, and if the call is going to deopt, you jump to here first, and he does things.
So we debated the alternative where basically a deoptimization code path is just an explicit edge from a call.
Yeah.
And there is arbitrary code we can generate.
I did that for escapes, not escapes, catches, catch handlers. If you're throwing out a call, you went to this arbitrary point. It was a multi-way control, but not deopt.
We called this idea deopt as exception because it's very similar to exceptions, but
right.
you are required to deoptimize instead of resuming normal execution.
Yes, I see. Deopt as exception.
We didn't implement this, and we see two issues with this. So first, instead of having this DSL that describes what you do on deoptimization, you basically have your compiler IR, so you can move things freely. That's great. But then the native code you would generate will be less compact than the DSL, and there are a lot of deopt points. So it just bigger amount of this metadata.
Yes. Right. You get a big fluffy code for the deopt, and C2 would take I would say shortcuts would not try hard on the deopt paths to like register allocate or spill or whatever. So the deopt code would be fluffier. And so you get, and you have a lot of them. So it's not executed code typically, but yes, a lot of fluffy code for that.
And the other concern, it was theoretical. I don't remember ever coming up with a specific example, but the problem that can happen is when you are required to deoptimize on return from your colleague, it is because the code you have in this compilation is no longer valid because some of the assumptions you took are incorrect.
Right.
So what prevents you from making an assumption in some like fast path code, syncing the modified code into the deopt handler?
Because the deopt handler takes the correct valid state with all assumptions in place, with all the correct assumptions in place.
Yeah, but if your deopt path is just an edge in the control flow graph,
right?
What prevents, and the optimizer is free to move the code.
Like, just what I said. He takes only the correct path. He takes only the correct info. He builds a valid, correct interpreter state for where you're at in the current execution period end statement. It is correct for that point in execution. You made an assumption that there is never subclassing of the foo object. A subclass appears, you static inline, blah, 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 whatever. But at the deopt point, it's only ever have a foo object.
That's how it works now, and that works. What I'm saying is, if you allow arbitrary movement of code,
that's what I'm saying. It's not arbitrary. It's what moved into the deopt is what would you need to build a correct state.
Well,
but so if I'm following correctly, so you've got a loop, you've got some save point in it, and instead of representing the save point as just some thing in the loop, you effectively treat it as like the save point like branches off to somewhere else, and then now you can sync save point relevant data, save point relevant like unpacking of state into there. So then it's not in the middle of the loop, right?
It's not even about save point. We can take even simpler example. We just have a call, and this call we can deal. This call is a save point, so we can be deoptimized on the return from this call.
Okay, Arthur, I'm writing code. Pick a code block below and write your code.
All right, but
because I think an example here is like interesting. And I'm just skipping headers and things. Right, I'm just going straight into while mini. I have
I'm using the block below. I don't even need a loop. Like I'm using just.
Oh, I see. Okay, yeah, fine.
And this is my deopt state, and my stack is something. My local is something.
So somewhere in the world, there's a hidden. I don't know how you write hidden code here. If deopt and then else, it's bar is here, except that bar the deopt has no code at all. And then bar, you want to do something fancy like inline illegally because it's foo.bar. And foo has no subclassing. And instead of a virtual call, you call food, and then foo is inline.
Let me finish with the example.
Finish your example. I'm trying to help along.
So this is the standard way how I think C2, Falcon, Graal, I think represent the deopt state. The other way we can have a separate control flow edge on return from bar, similar to how there is an exception thrown edge. We can have like
that's a better way to think about it.
Deopt, and then we have deopt block, which literally populates your buffer. Like there is, I don't know.
Kind of.
And then.
Right.
So this is an alternative way to implement this. The nice property of this is, for a compiler, it is just another edge in the control flow.
Right.
So if my I don't know S1 is a result of some like I don't know, I have some call here.
Right.
And I use it here, and I'll copy it here. So in this case, there is no in the classic implementation, there is no more syncing opportunity. Like, okay, we have to compute S1 here and just use the value.
Yes, and of course you want to sync it, and you can generally sync it.
But for this Deoptas exception, we can actually do something like this.
That's what I'm saying. This C2 will do that right there under the assumption that compute S1 has no side effects that bar depends on. So you said compute as a function call, but it's actually an expression with no memory updates.
It won't do this because like there is no way to encode this unless you generate custom code for this Deopt block.
No. This is all standard, comes out of global code motion. So I'm like I said, no side effects. I'm going to replace compute S1. Can I hack your example, or should I make my clone of it for my own example here?
Let's do a copy.
So I'm going to replace compute X1 with a known expression. This is an expression only, no side effects. Okay, C2 will just sync that expression down into the Deopt path. That is the normal way.
Where is your Deopt path when you are dealing with just a call?
It's in the IR. It's the okay. So in the IR for the case where I'm doing catches, I didn't do this for is Deopt, but the same exact strategy works. So if there is a catch here, then the Deopt block is the catch.
For explicit exceptions, yes, that's how it works. But yeah, I'm talking specifically about deoptimization. Like someone
just for Deopt, it would be exactly it's an edge in the control flow graph. Where it gets laid out in the code space is just wherever the code layout throws this block. This is essentially
at least now in both Hotspot and OpenJDK and in Zing, there is no extra code that is generated for Deop.
No, it's correct. There's no extra code here. That's the point. There is no extra code. It is the same code. You're saying, oh, I made a clone down here or something. No, this is where code motion happens. The expression just got moved in code motion. So you have in the land of Sea of Nodes IR, this on Deopt block, this is turned into in the IR, it's an if. If oh god, somebody keeps typing and it hides what I'm writing. If Deopt fail it looks like from the IR's point of view, and then you have some code over here. This code will be B equals expression. And then that will be fed into the call Deopt as a hardware jump into the VM and never come back.
Do you remember the knob sledding mechanics of deoptimization in Zing?
Boy, I mostly yanked those.
Well, but no, this is how we do this to this day.
Yeah, well,
because you're doing knob sledding, there is no code you can execute. There is no block. It's
right. Knob sledding. Okay, there were different fail outs. Knob sledding was only useful in certain situations that said I couldn't come in.
Yes, and that's the example I'm talking about. Someone changed something in the universe that made us no longer correct. This compilation is no longer correct. We cannot resume execution.
Yeah, and like I said, I yanked knob sledding because I wanted to jump for the Deops. Knob sledding says I can't even do that. Well, no, the Deopt points live on in the code, and they're taken by a bunch of folks that say no code is in the main path, but you did a table lookup on a fail and jumped over. Happens for all the catches. Could happen for Deops as well. Knob sledding says, yeah, I can't. There's no code. You're correct. If it's knob sledding, there's no saving. I can't do this.
Yeah, that's the scenario I'm talking about. We are
Okay,
doing knob sledding.
like I said, I yanked knob sledding because it was not necessary.
Well, it's there. It's the main mechanism of the optimization.
Okay, well, you can't do this. It goes into a DSL. I would claim I would turn around and say knob sled away, but put all this deopt code to the end and jump to it, and it doesn't get sledded. It doesn't get knob sledded.
But okay, so
But fine.
you're saying you had this basically deopt as exception way where you have a control flow edge and you
Yeah.
had some block where you could sync the expression.
Yeah, yeah.
What prevents an expression that is computed under the assumptions that the compilation made?
Yeah, those things have to be under this expression is valid here.
Yes, but it is valid under the assumptions that are required for this compilation. When you are being de-optimized, this assumption is no longer correct.
No, it fails here. But it was valid here and it has no side effects. So it's always safe to compute it ahead of time, behind of time, sync it. It's functional. It's purely functional.
Wait, so let's imagine, I think I know what Casey's getting at, but I also figured that it wouldn't work this way. So like, let's say you had some, I don't know, somebody loaded a new class and it like violated some assumptions. So you say, okay, I need to bail out. When you do that, you're gonna have to walk the stack and you're gonna go to every single deopt point. So you'd like your call is gonna be associated with this like deopt branch looking thing.
Yes.
Except it just says like go run that code. Cool. So you jump to that code, and then in that code, wouldn't the assumption still be true until the code is finished unwinding?
Exactly.
Yeah, and in which case,
exactly the point. So
and then once you're
I
done,
wrote valid here and fails here. It means that expression was valid in the in-between state. When it fails at bar, it fails before the code has been made invalid.
Yeah, exactly. Because you need to invalidate all the stuff before you can actually like touch it.
I think I have one example which might be incorrect. So one of the assumptions that we make now is that some fields are final.
Right. Well, you actually do that. I tried that and it failed. So many different people failed me and I gave it up. But fine. Yes.
Oh yeah, we pushed through and we do the invalidation of this. But let's say we had a load.
You want to put a load there, right?
And then let's say
you're going to move it down into the deopt block. Yes.
Yeah. Let's say my v2 is just another load from that field.
Right. Now you have a dependency on v1 of that field being final.
So I think if I don't tell compiler anything.
The compiler has to tell the runtime, I depend on this field being final. So he does this. That's fine. And depends on v1 being final.
That's
the load
right.
is final.
But then when I am executing this code path, this assumption is no longer true.
No, it is.
So no, the assumption is going to be true up until so it needs to finish doing the bailout before it can do the write to the final. Because if it did it before, then you would break your assumption.
No, it doesn't work like that.
It does.
I think what he's saying is like it kind of has to. So like you have to first stop everyone, and then you can do the breaking thing. So like for instance, like a TLB shootout or shoot down or something, you have to like stop everyone, do the modification, then everyone else can
This is how it works right now, or everyone is dead already a long time ago.
Wait, no. So your bar, I don't know, somehow.
Your bar does something, loads a class, and the final field is load from some final thing. I don't know. Final field. He breaks final field, right?
It writes into final field for whatever reason, using reflection.
Right. He reflection final fields. Correct. Now, when you say reflection, damn, you're dead. Stop. Don't touch final field. Don't mess with it. Deopt. Okay. You run through, you go read that final field, you've read it already, it's still final, hasn't been modified, you take that value, you deopt.
But wait, it doesn't work like that. You don't touch the frame of foo until you return there.
No.
No. So what would end up happening is for final field to write, you have to have everyone who could have touched final field needs to deopt so that you can say, I can safely break the assumptions that I was doing, and then final field writes, and then everyone else can start again. And when they start again, they'll check and say, hey, final field is written, so like all my stuff is invalidated, or maybe like the final field writer thingy says that everyone's invalidated. Whatever check does that, by the time that everyone else runs, there's like this fence in the middle where like the assumption is being broken, and before the assumption is broken.
It doesn't work like that now. It only does the deoptimization, like replacing of the compiled frame to interpreter frames on return to the frame that got affected.
Yeah, I hear you. So let's work through what's going on here, because maybe there's an issue we need to sort with finals that didn't impact me doing other things.
Yeah.
Your example as written here doesn't fail because the final is loaded before the fail. Then you use the loaded value down below. That's okay. That is correct. But instead, if I load my final here and I've dropped it from above, so this gets sunk. Then what happens is I should have loaded it up where it is pre your modification. I do load it after the modification. I'm dead. Okay. And then now, okay, let's work through this one because this doesn't happen when I do calls and catches because I do this all the time.
Oh, with catches, you don't. Nothing gets incorrect about the code that is executed in the current compilation. So catches are.
Oh, I see what you're saying there. But I know C2. Oh, C2 drops all things that are known to be functional down in the deop path. So if you loaded a final field, here it is. The final field has to load here because the bar new for your use case. No, not new, actually old. This is all correct. I gave up on final fields. Final fields load here at V1. They do. I'm not going to sync the load of the final field because bar will anti-dep and write it. I assume the final is a lie. Bar will write it. Therefore, it's an anti-dep. Therefore.
But that's the whole point of this speculation, that you assume that the field is unmodified. So you are taking advantage of this assumption.
Right. Remember, I tried final and I gave up on it because people were modifying it. But if you were going to do this, so you wanted to do this hack where you load the final down here, perhaps, so like never load it in the hot path is what your goal is. And bar wants to come through, then then now you need a different deop strategy. Or one that says I'm not syncing the load of the final.
What is interesting, if you are doing it just after the call, not in the deopt path, and you assume that the field is final, so you'll just reuse the value of V1.
Yeah, right.
And bar modifies your field. It's all good. On return, you say, well, my code is no longer correct, so I will take the interpreter state, reconstruct the interpreter frame.
Right. And that's because
the problem is if you try to sync arbitrary code into these code that is executed after the assumptions are invalidated.
I'm saying I did this for catches all the time, and I do it for functional things.
Catches don't invalidate the code.
And functional things are already computed and are correct because they were computed before the failure. So I can sync anything that's purely functional. Any set of math, array lookups, not array lookups, array math, and all kinds of shit like that gets.
Wait, so to clarify a bit, if you had, let's say, you loaded a new class and it invalidated stuff in hotspot or in like Azul stuff, if you did that, it would stop before it would basically stop so that I can go and say, hey, I'm gonna need to invalidate a few like different code buffers that all depend on this.
And what Arthur's saying is the deopt is lazily done. It is late in life because bar did not inline. Since bar did not inline, bar is allowed to finish the job of whatever bar normally does. So the deopt is not happening. And this, by the way, is another thing that we could argue as a different path forward. Bar is allowed to reflect, modify final, but foo is not allowed to complete because he depends on the final. But bar is allowed to complete. That is one strategy. There's another strategy that says that bar is not allowed to complete and everyone just goes to the interpreter and then we're done.
Yeah.
But if bar is allowed to complete, and it typically bar is hot, doing a lot of things, inline's more shit, you're deep into bar running a long time, you want it jetted down in there. When you unwind from bar back to here, that unwind from bar stops and says, if you're knob sledding, you slide to the end and you do your table lookups. If you're not knob sledding, you jump to this, return stack patching is what I was doing. Return stack patch.
So sorry, what is knob sledding?
Fill the method with knops such that when you return, you execute knops to the very bottom of the method. You slide, you sled to the bottom, like sliding downhill. You do nothing to hit the bottom of the method, and then you jump off. You put one jump at the bottom that says, go figure out what the fuck just failed.
Gotcha.
Okay, that says no code following the bar call executes. That's that strategy. The jump stack patching one is one that says the return from bar into foo gets patched. So when I return to foo, I actually return to the deopt recovery handle for foo, or the catch call recovery handle for foo. And then the question is, since bar executed and he modified that final, I shall not be loading the earlier final V1. I shall not be taking the final I loaded above as a CSC example because I need to reload because the final wasn't final, it got modified. Yeah. So the way that's normally done in C2 right now is I don't treat finals as finals. Then you did a load up here and you did a call to a bar. So another load is unrelated and I have to load again because bar stomps it, which in fact it's going to do. The optimization for final says, oh, geez, we know V1's final and bar will do something about it. My cat is coming to announce that he's dying of starvation. He knows that he's final and therefore, we can reuse it later in life. But if we fail, something special needs to happen. And we've noticed that V1 is not used. I had to load it. It's going to get used on the fail path only. I want to sync it down in the fail path and not load it in the main path because no one uses it. Yes, come up here. Come on. You're not starving. And now the point being, I cannot load it after bar modifies and returns, or I have to, that's not the right answer. I have to load it. I cannot reuse. So if I found this value here, I know this path wants it, but in fact, it was CSC down here, but dead over here. So I just sunk the load, the loaded value, but I wanted to use it up here. I don't know how does this fail again? If I load it up here and I reuse it, I'm in trouble. If I load it up here, it's not dead. And if I deopt, I just want to reload here. And I want to claim on the deopt path, the deopt code won't sync the value because it'll be treated as a new load because bar is failed for rewriting final, and you won't get this path. So I'm back around to saying it's not a broken thing.
Wait, but because you assume that bar can modify the final field, but the whole idea of the optimization that we want to assume that it doesn't.
No. On the deopt path, I totally assume it's modifying the final field, not on the other path.
You need to basically teach the optimizer that this edge is special, that you might have some side effect on this edge that don't exist on any.
That is totally what happens right now for those edges for calls and catches. It's a special edge. You throw an exception.
Even so, that's not a particularly special concept. You probably just stick a control dependency on it and say this one is not the same as this other load.
No, I'm not touching the load with dependencies. That's a no-go. Instead, I know that when I took the rare path to one of these off jumps, some assumptions changed on me. Like I have a catch of a class I knew didn't exist, couldn't have been thrown unless you loaded a class. So on the code on the off path, I give up on shit I know about on that guy.
So ultimately, there is something special happening on this edge that doesn't happen anywhere else. Like some of the assumptions that were valid everywhere else may no longer be valid.
Yeah, I throw cast in here that says you fail. So there'd have to be a weird piece of code added for deopt on final. That's not present right now. But
it also means that you're probably not free to move any code into this handler.
You're saying move. There's no move in C2. There's no move code. It's all global code motion, and there is no placement at the time that we're doing this kind of shit. There's no motion.
But conceptually, once you schedule, it is.
Yes, now it's all about the dependencies and scheduling. So just track dependencies. if I say I have a final field, but I don't know shit about final, anti-deps, the load happens early, it didn't move down into the off branch. Okay. If I say it's final, but I have a fail on final, then I'm going to say this load and this load aren't the same because the memory state changes on bar, therefore they won't CSE, and I'll just get a separate load here, and I'm also good.
But I don't understand how you can model this, that if you I feel like you will have to basically model your dependencies also as edges on the graph. Because
all my depend. But that's exactly what it is.
No. I mean deoptimization dependencies.
The deop dependencies that only this is a new thing I don't have, and I'm saying here's how I could do this.
Okay, that's what I'm saying. You will have to introduce new type of dependencies in your graph.
No. At the time the parser parses and he comes to bar and he's building the graph as he goes, his bar is not getting inlined, and I have a final field thing. Then when I have the deopt for the final, I have to put in the path for the fell through. I have to put the path through the catch of the this and the that and the other. I have to put in the deopt path. Okay, I'm putting the deopt path in. On the deopt for final, I'll say it's not final, and all that means is I'm not going to reuse the same memory edge that fed the load. I'm going to use the memory edge that came out of bar, which exists. It's there. I have it. And I'll make a load off of bar for this other path. Well, that load won't CSE because the memory edges are different. Done. Okay. Literally, there's nothing going on here.
You solved this specifically for the for this type of compilation dependency.
I'm saying yes.
The general problem is still there. That the assumptions you have everywhere else in the code are different than in these blocks.
It's the time I build IR, I'm throwing in all dependencies. So at the time I build IR, I have to be aware of the dependencies. But at that point, there's nothing special about the dependency edges. They look the same as every other edge. There's no special thing.
You don't track deoptimization dependencies in the IR.
I do not now because I do catches, but the deop dependency would be a straight up thing to add. And it would say things like, why did I deopt? At that time, the parser has to say, here's an assumption that no longer holds. This parser has all these damn assumptions right there. They're baked in how he parses.
Yeah, but they are currently global for the compilation.
No, they're not.
Well, they are. They are like baked into the types. These refinements.
CHA comes in and says, I knew this, but when I hit a deopt on a catch of a class that didn't exist, you betcha I throw a cast in that says, oh, now you're casted to something that's not there. And then that blows up everybody's afterwards, and I can't do shit about it, and I get no optimization in the off path for the catch.
Oh, but let's take the CHA assumption.
Yeah.
If I remember C2 code correctly, it refines all the types using CHA. If there is a single concrete implementer, I think it would go and refine it, and it will use these types in the type lattice everywhere, right?
And as soon as you hit a bar that can throw, and you have a call that has the multi-way jump operation after it for the catches, on each of the failing catch paths, each of the catch paths, the type of the this pointer is whacked.
I'm not talking about this. I just in general, it's this assumption is hard coded in the type system.
It's the same for all of the other things. All guys of whatever type got failed on got whacked. Their types get whacked because I say, hey, I know that this happened here. Now, if I want to do this for deopt specifically for certain things, I would have to add a whack for each kind of thing that I made an assumption I'm failing on. So final field would say no longer final.
Let me have another example. I think I can think of. Let's say we have a Boolean value that some object instance of the base class. And now using CHA, you say, well, I know that base only has one concrete type.
Right. So use boot. I don't care. Pick your name. Yeah, don't say concrete, but say food.
No,
But yeah, I get it. Yeah, he's some
you can
concrete.
check that it
Yeah.
translates into get kid of object.
Yeah, no,
It's
you're
literally
doing a test, however that's done.
your concrete. But let's say this value C is only used in the deopt path. Like, I don't know, my
Right.
my local is C. So what prevents?
And the deopt path means that you had code that you didn't do, that you asked an instance of question using am I an instance of a base or a concrete, and you had some code that you're going to deopt on, but you had code there.
Wait, I
That
have bar.
code had to
I
be
have bar.
valid at the value of object before calling bar.
So we have this check. It computes C.
Yeah.
The only user of this C is in the deopt state for bar. Like,
So there's some code that follows bar that we're going to jump to the interpreter on, and that code that follows bar, for instance, it's on a catch clause because you took a deopt jump. You had to have some code there. If you're just falling out of bar, that's not a deopt path.
Well,
running code.
Yeah, let's say it's on the exception throwing path, but whatever. For some reason, I in the compiled code I removed the use of C, but for the interpreter I will need it.
Yes. Yeah, there's a thing where I say shit's alive for just the interpreter in there, and then I keep it around.
That's this case. So now, what prevents C2 from
says instance of base? You're saying I've promoted C to concrete.
Yep.
Already.
So what prevents it from scheduling this check, this comparison, in the deopt block?
The load of the subclass of base. Oh, I see. When you come out of bar and you're in a catch, the obj has been allocated already. Obj predates bar. Obj will never be an instance of anything other than concrete. It is valid to sync it. Objs, sometimes everything's functional. So obj is functionally done. I have obj. It's known to be pre-bar, therefore it is known to be concrete. I'm good.
So yeah, and here we
yeah, you can't change obj without doing a load. That's memory state. Memory state get crushed by bar. I didn't do it. I didn't sync it. Yeah, you wrote concrete too. Right.
Yeah. I'm loading another implementer of base, so I'm actually invalidating this thing.
Well, you wrote instance of base, which you are. You need to say instance of concrete, where there's a base and a concrete, and the answer is yes. You must be a concrete. Yes, so change this to be concrete here. I'm trying to help with this example.
In the original program, it is base, and this is the optimization you would do, knowing that there is only one concrete implementer of base.
Yeah,
you would rewrite the type check.
Yeah, so obj is known to be concrete at this point in time.
Well, it's either concrete or like something else.
No, I did CHA. If base is an abstract class and there's one implementer concrete, I will have promoted object to concrete.
Okay.
That's what CHA is gonna do. And this is a useless junk test because C is known already to be concrete. And this is like object. Where did object come from? You're passing it in.
Well, okay, it will get optimized to this check.
Yeah, it'll be optimized to something, and then say I see what you're saying. Is you're just asking, you're trying to get a Boolean out of this?
Yeah,
Doesn't matter. It's all good too. Right. This is a fast, easy, quick check. I must be a concrete thing. C represents that value. Okay. It's all functional.
And then I'm saying, what if you sunk this check, the optimized check?
Yes. Down
into the deopt handler.
Yeah, the optimized check is functional. It has no side effects, depends on nothing. It's pure. It depends on nothing. It's correct as it stands because obj was not crushed by bar.
Okay, so what saves you is is the fact that you are using the value that existed before.
Yep. And that's what I'm syncing. All along,
But-
I'm saying I'm syncing functional things. I'm taking all the values that came before bar. They got sunk.
But then, well, let me do this. Let's say bar returns you a value.
Yeah, as soon as bar returns me value, all your problems, I mean, all bets are off.
And now you are, so, oh, okay, I think I have an example.
Okay.
Um,
As soon as you get side effects like bar returns me value that I depend on, it didn't get sunk.
but wait, but then I have some code on that code path that takes that return value and
Right.
makes a type check.
So hang on. So I'm going to make your example a little more realistic here. If where I'm off to the side path, because the standard thing is bar calls, I never execute this.
No, I'm talking about explicit deoptimization, like NOP sled style. We are invalidated.
Right, but I'm not. In order to do a deopt here, I only need to deopt to the interpreter things that bar takes in, nothing that bar returns.
That's not true,
Yeah,
because when
bar's not returning.
When you're reconstructing a state after return, the top of the stack will be the value that your call returned.
Oh, you're saying a deopt here. But that's just a weird thing. Yeah, it'll be the return that comes back, but nothing's in the deopt state then.
Well, but it is a part of the deopt state. The return value from a call
Yeah,
is
but the
a part
return
of the deopt
value is, but I don't do anything with it because of course I don't have it. So there's nothing, there's no use of it down in the deopt code. I am trying to build the interpreter state for a return from bar, which will contain everything that was in the interpreter prior to bar, and then the return value from bar. But
Yeah,
I don't do anything with the return value from bar. That just gets patched in by the deopt path already.
Yeah, I don't see how we would have this specific check, but well, let me summarize the whole idea that we are making assumptions in the deopt path which are no longer true.
No,
make me uncomfortable. Like,
okay,
I
I claim that is not the case. We are not making assumptions in the deopt path that are no longer true. It is the case that we are moving purely functional code whose inputs are all available down into the deopt path.
But what prevents some later optimizations from making these assumptions in the code that we moved?
That's what I'm saying. It's purely functional. Those assumptions had to be valid before bar. And then what the optimizer does, what the optimizer does. He optimizes functionally based purely on what he has, dependencies in front of him. But it was all done before bar. It's all used after bar. He can delay it, but it's all functional, so delay's fine.
All right. Well,
you were trying to say something about
what if I
but it's not obj. The next future call to foo, not the current call, a future call to foo, obj comes in as a concrete 2. But in this call to foo, obj is limited to being concrete. So I can sync the instance of check down into the concrete path, down in the deopt path, because obj is going to be a concrete, not a concrete 2. And that is a thing that future calls are broken, but the current call is correct.
I don't see the fundamental reason behind why it should be correct. Like I see we are lucky. I see it as lucky.
It's not lucky. It's functional.
With specific.
It's just like it's like Greece got everything you knew about programming kind of shit. What the hell's the right word here? It's functional. I have the inputs. Nothing bar does can destroy my inputs. They are there. They are value objects. They are untouchable by bar. And if I move them down here and do some math with them, or move the math up here and do some math with them, they're functional objects. I can do math with functional objects and get a functional result. Nothing bar can do can touch these functional values. It's like you're making it harder than it is. It's just that simple. Nothing bar can do. No amount of code loading, no amount of anything can touch what I already have. The history has been done. I have it already. If I do math with it later, I do math with it now, doesn't matter.
So I think if you sync, I think if you sync something that existed in the code before bar,
which we were trying to do a bunch of cases here.
Yeah, I think
like your load of a final or the object instance of base. You have computations of things that were getting optimized prior to bar. But this first thing is those things were all available prior to bar. They were correct at that time, and I have them. I don't go get magical new state from inside of memory. That would be a definite fail.
Yeah, I think the problem, we'll definitely have problems if we start generating the code that didn't exist before bar.
I do that right now in all of the catch clauses. Code that exists before bar.
Catch doesn't have this property of invalidating assumptions.
It does. It's not. Well, it does in the sense that I got here because you threw an exception because you loaded some random thing.
Yeah, but it doesn't make your method fundamentally incorrect that you can no longer execute.
No, but it almost always happens that when I'm throwing the exception, it is also the case that I got here because I loaded a new concrete class as part of the whole shebang. That you bar through because you had some stupid thing happen deep inside nested bar, deep. And that path loaded a class while busy throwing an exception. And now bar is not bar, but something bar called deep, whatever, invalidated foo. So that happens right now all the time. I compute things ahead of the call to bar, and I take a deopt path when coming out of bar because of a catch. And all the things that happened in bar and below, they totally invalidated future calls to foo, but the current call to foo is correct. And I pre-computed shit from before bar. And then if I did that math on it afterwards, I did. I don't reload anything that bar could visibly change on me in the deopt path. Please come up with an example for next time. I'm totally willing to go through this. This has been working for 25 years. So I'm saying
well, at least currently, neither Zing nor Hotspot do this kind of deopt as exception style.
Not deopt as exception. That's correct. But it is exactly the same as I took an exceptional path that took an indirect jump for whatever reason.
I disagree. I think it's two very different scenarios.
All right,
exception throwing, sure, no problem. You don't invalidate assumptions, so you don't.
Totally. I'm inside bar. I loaded a class that that blew the assumptions on foo. I then threw an exception. I came in on an exception catch out of bar, but I also blew all the invariants in foo. That's what I'm saying. Right now, both happen.
You wait. I would assume you would need to deoptimize in this case.
Well, that's what we're doing. I'm going to go to the catch clause for bar, which almost surely will rebuild an interpreter state and then call the interpreter, who will then throw. I will deopt into the interpreter, yes. This is very, very commonly the thing. You can have a catch, I'm going to handle the catch, actually handle and not actually deopt, but that's not common. The common case is I'm going to deopt here.
Well, yeah, anyways, I don't think any of the compilers currently do arbitrary code motions into deopts.
You can look at C2 code. He'll sync functional stuff into deopt paths all the time. He's been doing that forever and a day.
But no, no way it can be done.
I fucking live with it. I wrote it. I dealt with it. I watched it happen. I made sure it happened. It's totally there.
It doesn't happen today.
I bet it does. I bet you're just not looking hard enough.
Nop sledding kills all the code.
If you're going to nop sled, that's okay. Okay, fair enough. If you're going to nop sled, you don't get that. So you're correct in that sense. Like I said, I totally yanked nop sledding on. Well, we tried to push it back at Sun. They didn't want it at Oracle. I killed it on the main path at Azul. It might be back now, but it was gone for a while. And the deopt guys took all sorts of things. In fact, they would still take all sorts of things. I don't understand. You had to have unwound something for knob sledding to be correct, or knob sledding only happens in a certain situation because C2 does code motion with global code motion on deop paths like everything else. And if there's no dependencies, that code's going to get sunk and it's going to be on the deop side. So you have to run the deop code to get an interpreted state.
Well,
What does global code motion mean in that context?
It's the standard global code motion algorithm in simple right now. Only you move code only to where the dependencies need it. It has a range, a spectrum of positions. You choose based on frequency. Deops get the, your frequency is super tiny. So everything I can move into super tiny frequency gets moved there. Even right now, unless, like I said, unless something really bizarre is going on, shit gets moved in the Deop paths because if you do math, so you loaded two fields, whatever, and you added them, and the add is unused by anybody except the interpreter on a Deop path, then the add will sync into the Deop path. And now to build an interpreter state, you have to like add register 1, register 2, which, knob sledding going to do it. And the DSL for describing interpreter state doesn't have shit like random math, like adds in it for my stuff, for whatever C2 was. Arthur's saying they've added a bunch of stuff. That makes sense. But if you knob sled and then you ran off the end, you didn't execute to the interpreter there. I bet you blew out even, you bet knob sledding is only applying when you're actually going to blow out even the rest of foo. And you're not going to go to
That's so this is for the case where some assumption is invalidated. We can no longer touch that assembly because it's incorrect.
But I bet you it's also for the case where you don't even finish the foo method in the interpreter. So that's why you don't even bother with a deopt path. You're not going to finish the interpreter. You're going to throw out of that method, out of foo in the interpreter. Like jump to the interpreter in foo and then throw out of foo. Why jump to the interpreter? You're just going to throw out.
Oh, no, it's still possible. Like let's say CHA invalidation. I would resume foo in the interpreter. There is no exception being thrown.
Yeah, okay, but I bet you're not knob sledding there.
We do.
I'd love to see because that should be broken, and you break everywhere. You cannot possibly run code this way with C2. Now, if you're using only Falcon and you go to C2 and C2 is something different, I don't know.
So
But I'm saying,
was there before. So we
guarantee you.
Knob sledding was there before Falcon. That was the mechanism of deopting.
I went and yanked knob sledding so I could have things, well, because it was a senseless operation for a bunch of things. But and there were some paths where it lived on, and it's all fine if you're throwing out of foo. If I'm coming into foo, I want to execute no code in foo, and I'm going to throw out of foo. Yeah, I can knob sled. I'm not going to execute that interpreted stuff, that functional stuff being fed in the interpreter. It's all dead anyhow because I'm throwing out of foo. But if I'm going to catch in foo and run on the interpreter, I'm not knob sledding. I'll bet you I'm doing the stack patch. That's in there, unless you've yanked that too. And then
we reintroduced it. We introduced it some time ago for some cases where we don't want to kill the code blob. But again, it wasn't there before.
I certainly put in return patching before.
So, well, I guess it's been a long time, and the code evolved. Like many different people touched it, so we probably thinking
how long
is
C2
the same thing
there. But C2 and Sun will surely sync purely functional code in front of Deops. That's just, it's been doing that for 25 years. Unless Sun's hacking that too, it's definitely going to do it.
So I'm not that confident about the one in OpenJDK, but I was under the impression they have similar way to encode the deopt handler, basically.
Yeah, it's like this register went here or there, and simple constants was what I had when I left Sun. Nothing that would do like multiply two things together, but they might be functional, and then because it's just a multiply, and they might only be used by the interpreter. And they are used by the interpreter, so they're in the deop state. But the main path says for hot loop, multiply dead, but the interpreter wanted it because the interpreter too stupid. It would sync into the deop path. No question about it. That's what I don't get about what you're saying here. If you then knob sledded this function and you wanted to continue execution in the interpreter after knob sledding, the interpreter wouldn't get fed the multiply of whatever.
So yeah, what we have is we have knob sledding. We use DSL to describe what to do after the optimization, and we do the syncing, but only syncing into this DSL, which is limited to like what kind of operations get sunk.
Right.
Maybe at some point in C2 you did have this Deoptis exception style. So maybe maybe
at some point was as far as I know, running forever because all catch clause behaviors went this way. So everyone who threw didn't inline and was going to catch and carry on or catch and throw again or whatever. If you were doing something, you hit a deopt here, and that was not knob sledded. If you were blowing out, you could knob sled your way out. But if you were going to catch and continue, you went to essentially like your deopt example, you went to code where I came back from bar. Now, the bar return didn't happen because it was a catch, but the inputs to bar were all valid interpreter state. And now I'm in the handler code, which, 90% of the time deopted again, whatever. All right, I think we have agreed to disagree. Our memories of history were 3 hours long. And it could just be that the state of Azul moved one way and the state of OpenJDK moved another, and I walked away 25 years ago. So, hard to say what is what and where is where. If anyone watches to the end and they get here and they know something, feel free to throw comments around, and we'll see if we can't sort the mystery here. All right. Well, fun conversation anyhow. And it would be nice to get sorted out what it means. But moving stuff down the deop path versus knob sledding, I didn't like knob sledding. I understand why it was there, but fine. Okay, done. I need to eat. My cat wants me to feed the cat. Cat gave up and is waiting patiently.
Yeah. Bye everyone.
All right. Bye-bye.